Hello students, how are you all? So, I welcome you again on PhysicsWallah, and today we will start or learn the 7th chapter of 12th class, which is geometrical optics. And there is no need to tell anything about how important this chapter is, how scoring this chapter is. Okay. It has a big theory. There are many theoretical questions and many numerical questions that were asked in many examinations. Sometimes multiple questions are asked in same paper. So in this chapter we have majorly three phenomena that we study. The first is reflection of light. The second is refraction of light. Third is dispersion of light. When light ray traveling in a homogeneous medium encounters an opaque medium or a mirror, it is reflected back or bounced back in the same medium. So that is the event reflection of light. In reflection of light, we will study reflection with mirrors and also the plane mirrors and curved mirror or spherical mirrors. The second phenomenon is refraction. In refraction, the refraction means light traveling in one homogeneous medium enters into another homogeneous medium, and in this process light usually bends from its path, and that bending is called refraction. We study refraction at plane surface and also on curved surface and also through lenses and prism. So we study plane surface refraction PSR, curved surface refraction CSR, refraction through lenses and prism. That are the subtopics of refraction. What is dispersion? Dispersion actually happens when a mixture of light, or you can say white light, as white light is mixture of all colors. When this mixture of light of white light is refracted, it sometimes splits into its different colors. And this is the main reason behind the formation of rainbow. So in dispersion, the splitting of colors happens, and this we will study at last. Okay. So dispersion is also a very interesting chapter. Let's begin. When we study geometrical optics, we should keep this in mind that light in a homogeneous medium travels in a straight line, and its path is represented by a direct line segment called a ray. There is no need to tell this when light is bounced back or reflected back. The angle of incidence is equal to angle of reflection. This is angle of incidence, the angle between incident ray and normal. Angle of reflection, angle between normal and reflected ray, and they are always equal. This angle is called glancing angle, means the angle between surface and the incident ray. So glancing angle of incident ray is also equal to glancing angle of reflected ray. There is one more thing you should keep this in mind. All these three line segments means incident ray, normal and reflected ray, they all lie in one single plane, and that plane is actually perpendicular to your mirror's plane. If we assume three spatial unit vectors, one along incident ray, one along normal and one along reflected ray, there are three unit vectors: incident ray E cap, reflected ray R cap and normal N cap. Then if you understand the vector laws and you apply I equals to R, you can easily derive a relation between three of them, and that relation is actually written here. Let me write it again. The reflected directions unit vector is given by unit vector in the incident direction minus twice of E cap dot N cap. N cap is a unit vector along normal and N cap. Okay. So this is the relation between all three. Okay. And we have a question based on this. Recently in 21, they say here the incident ray, reflected ray and outward normal are denoted by three unit vectors A, B and C. So according to them, we have E cap as A cap, R cap as B cap and N cap as C cap. As these three are related as R cap equals to E cap minus twice of E cap dot N cap, if you replace E by A, R by B, N by C vector, you will find the correct relation among three is C. So C is your right choice. Let's move forward. So let us now understand the concept of object and image. And this concept I am discussing, it's not limited to mirrors only or reflection only. This will be a general concept and it will be used in entire optics, whether it is lenses or prism or plane surface refraction or curved surface refraction, anything. So it is useful for the entire chapter, the ray optics. So what is an object? You must have read many definitions of object, but that the definition which never fails and never confuses you is the object is point of intersection of incident rays. Point of intersection of incident rays is actually the object in geometrical optics. Okay, and similarly, the point of intersection of reflected or refracted rays. If you are dealing with mirrors, we have reflected rays. If you are dealing with refraction, we have refracted rays. So, after incidence, the rays are either reflected or refracted. So, point of intersection of reflected or refracted rays is actually image. But actually, there are two types of objects in ray optics. The one is called real object and the other is called virtual object. Obviously, incident rays are maybe of two types. Sometimes they are diverging and sometimes they are converging. Okay, so suppose we have diverging incident rays. If the rays are diverging, incident ray, remember, if incident rays are diverging, their intersection point is called a real object. And when incident rays are converging, we have a virtual object as their intersection point. Remember this point? Many people ask me how this type of objects are formed in nature. They are not naturally occur in nature. They are generally formed during optical events. Okay, during optical events they form. I may give you one example of it. Like, suppose you have a lens. Suppose this is one ray and this is the another ray. The two rays fall on the lens and they finally converge to meet at some point on the right hand side. So these are two rays. Okay, obviously the point where these two refracted rays meet is actually the image for the lens, right? But if we place a mirror here, these two rays which are refracted rays for lens are actually the incident rays for mirror. Can you see that? These two rays are incident rays for mirror. So this point is actually image for lens. This is image for lens. It is image of lens, but it will be object for mirror. Can you see? It is object for mirror because for mirror this point is intersection of incident rays. And as incident rays are converging, can you see? As incident rays are converging, this will be a virtual object. So this point is actually a virtual object for mirror. And also remember, if we have multiple optical events in sequence, means the first light is interacting with lens, then second it is interacting with the mirror, then obviously the image by first event becomes object for the next. The image by first event becomes object for the next. So remember this point, intersection point of diverging incident rays is called real object and intersection point of converging incident rays is called virtual object. Similarly, we have two types of images, the real image and virtual image. And the concept is, as the image's intersection point of reflected or refracted rays. So if this is the plane of mirror or any lens, and suppose these are refracted rays, how we recognize refracted rays? By arrows. Can you see? As the arrows are receding from the plane, this means they are not being incident on the plane, they are being refracted or reflected from the plane. So these are refracted or reflected rays, and the point where they meet is actually real image. So this is real image. So definition of real image is intersection point of converging refracted or reflected rays. And if after refraction or reflection the rays diverge, if the rays diverge, their intersection point will be called the virtual image. Okay, so remember these 2 points, they will be very helpful for you in future. Now we talk about the plane mirror. Plane mirrors is the simplest kind of optical instrument. Okay, and here we have only 2 cases. As you know, there are 2 types of object, 2 types of images. Okay, so there may be many cases, but in mirrors we only get 2 cases. In mirrors, the real object form virtual image. RO means real object, VI means virtual image, and virtual object form real image. Means the real object cannot form real image and the virtual object cannot form virtual image. The RO, the real, will always form virtual image and the virtual object will form the real image. Let us see how. As you can see, these 2 are 2 incident rays for mirror. These are 2 incident rays, and this is object for the mirror, as these incident rays are intersecting here. As incident rays are diverging, it will be a real object. But after reflection, these 2 rays cannot converge because they have to follow law of reflection. These 2 cannot converge, they will surely diverge, and if they are diverging, so diverging reflected rays intersection point is definitely virtual image. So here real object cannot form real image, it will definitely form virtual image. Okay, and suppose if we just flip the arrows, you will see the next case. Can you see these 2 are incident rays and these 2 are converging in fact. So if these 2 rays are converging, we have their intersection point as virtual object. And if these 2 rays are converging, after reflection they cannot diverge. They will simply converge at this point. And as reflected rays are converging at this point, their intersection point will be real image. So real object always form virtual images and virtual object always form real images in case of plane mirror. Next. There is one very important and very common knowledge, that the plane mirror is a perpendicular bisector of line joining object and image. So actually the plane mirror is exactly in the middle. It is exactly in the middle, and if you join the real object and virtual image, okay, or object and image, you just join object and image, the mirror will be, the plane of mirror would be actually the perpendicular bisector of this line. So this distance and this distance are always equal. Okay, the next point is all points of the mirror, means you take this point or this point or this point, any of the point, all points will be equidistant from object and image. That is the property of perpendicular bisector, nothing is spatial. And one more thing is field of view. What is field of view of image? The field of view of image is the region, is the volume of space where image is visible. So I think you have noticed, if you see your image in a mirror, the image always forms, but you may not always see the image. Like if you have a mirror in your room, you are standing in front of the mirror, you can see your image. But if you shift a little, image still forms, but you may not see your image because you are out of the field of view of image. Let us see what is field of view of image. So if this is your object Obviously, this is your image. And we will draw two extreme rays which are falling on plane mirror, and two extreme rays are being reflected like this. So these are two extreme rays, two extreme reflected rays. Okay. If you draw any other ray, it will definitely be in this range. But if you draw a ray outside this ray will not fall on the mirror. Can you see that? And it will go like this. It will not be reflected. So it will not participate in the image formation. We can ignore it. So this is the only region where we have reflected rays. And if we place an observer anywhere in this region, here, we place object here, observer, I must say observer. If we place an observer anywhere in this region, the reflected rays will enter observer's eye. And if reflected rays enter observer's eye, the observer's mind will experience the reflected rays are coming directly from this side, from the image. So the observer observes image here, right? So anywhere in between this region, the image is visible because observer is able to see the image. If you place an observer outside these two extreme reflected lines, this observer will not be able to see the image because the light from image, or reflected light I must say, is not entering his eye. Okay, so if you want to draw the field of view of image, just what you have to do is make an image and join image point with end point of the mirror and extend them, and all reflected ray will be in between this region. Okay, so that is about the field of view of image. This is a very popular question, that the minimum length of mirror required for a person of height h to see his full image is half of his height. Now let us understand its solution. Suppose we have this dotted line, and this dotted line is actually the plane or the wall where we are going to install the mirror. Okay. We have this, a man, let's say the height or the man is AB, and at point E we have the man's eye. So this is actually the observer. This E point has to see the image. Okay, obviously. If this is the plane where you install your mirror, obviously the image will be formed on the right hand side of the plane here at equal distance from the plane, and the image would be A dash B dash. Okay. And who has to observe the image? The eye has to observe the image, not me. This eye of the man has to observe the image. So actually the A dash point should be visible to eye. Means a reflected ray must come from, or must appear to come from A dash. Then only I can observe A dash. Obviously this ray is coming from A. Let's do not draw that, because that is only important thing for us. And I, this E point or the I point has to see B dash also. So obviously it can see B dash only if the reflected light from B dash also coming to I directly. Remember, these lines are actually reflected lights. These lines represent reflected light, and this line is not directly coming from A dash. They are coming first from A, and they are getting reflected at this point, and this light is not coming from B dash. Actually it is coming from B and getting reflected at this point. So at this point and at this point we must have mirror, because without mirror reflection is not possible. So here we must have mirror. So this is the region where we must have a plane mirror. Okay. As these two distances are equal, let us say this is x, it is also equal to x. Okay, and now let's do some calculations. If you assume this as P point and Q point, can you see the triangle EPQ and triangle EA dash B dash? They are similar triangles. And in similar triangles, all dimensions are in equal proportion, are in equal ratio. So you can say their bases, which are PQ, the ratio of the bases, that is PQ divided by A dash B dash, will be same as ratio of their heights. The height of this smaller triangle is x, but the height of this bigger triangle is 2x. So we have height of a smaller triangle as x and height of bigger triangle as 2x. 2x. You cancel this x and you can get PQ as A dash B dash by 2, that is h by 2. So we need half of our height of mirror to see our full image. But also if you install this mirror somewhere here, you will not be able to see your image. If you drop this mirror and this mirror drops here, you will not be able to see your full image. The mirror should be located at this specific location. And what is this specific location? By congruent triangles you will see the top point, obviously the two triangles which are formed here, they are congruent. And that proves that the upper point of the mirror should be in front of the middle point of eye point and highest point of the observer. Obviously, the mirror's topmost point should be in front of the midpoint of eye point and topmost point of the observer, and simply the lowest point of the mirror should be in front of the midpoint of lowest point and eye point of the observer. So that is the specific location of the mirror where mirror must be installed. There's one more less important thing, but you should remember this chart. Okay, suppose they give you a question like, we have two mirrors, and if we have two mirrors and one object between them, multiple reflections may occur and every reflection may lead to an image. So there are multiple reflections and multiple reflections produces multiple images. So how many images will be formed? They may ask you this question and you should remember this. Suppose we have two plane mirrors at some angle theta. What you should always do, always divide 360 by theta. Always perform 360 by theta and find a spatial number small n. Okay, find a spatial number small n. If this small n comes out to be an integer, what you have to do? You have to observe whether this integer is odd or even. Always remember, you have to check whether this integer is odd or even. If it is even, the net number of images will be n minus 1, that is 360 by theta minus 1. And if it is odd, there are again two cases. If it is odd, you will have to see whether the object is symmetrically placed or unsymmetrically placed. The meaning of symmetrically placed is, if this object is at angle bisector, means at theta by 2 and theta by 2 of the mirrors, this is called symmetrically placed. And if it is symmetrically placed, the number of images again will be n minus 1, small n minus 1. But if it is unsymmetrically placed, okay, the number of images will be equal to n. So remember this flow chart. If you solve this n and you find that this n is not an integer, it is a fractional value, then there is no method, no flow chart. You will have to draw everything by ray diagram and we will have to calculate it. Okay. Obviously the calculations are not involved, a lot of geometry is involved, so I don't think that is important for you. Can you skip that for every exam? Okay, even for JEE Advanced you should remember when n comes integer, that is the only case important for you. Suppose we have few cases. Suppose we have two plane mirrors and which are at 90 degree with each other. If theta is 90, your n will be equal to 360 by 90, that is 4. And if n is 4, means even, the number of images will be n minus 1, that is 3. Right? If this theta is 60 degree, if theta is 60 degree, n will come out to be 6. And if it is even, the n will be equal to 6 minus 1, that is 5. Right? If this theta is 72 degrees, then n will be 5. Right? N will be 5. And if n is 5, there are two cases. If object is placed symmetrically, means at 36 degrees with each mirror, or at angle bisector of the mirror, there will be, for symmetric cases, there will be 5 images, sorry, not 5, 4 images only, because n minus 1 images will be obtained. But if it is non-symmetric, then we will have 5 images, because the last 2 images will not overlap, they will be separated. So we will be having 5 images. So just remember this flow chart. This will be very useful if direct question will be asked. Okay, and let's move. So here we have a beam of light from a source L is incident normally on a plane mirror. Okay, so suppose we have a plane mirror and we have a source of light here L, and a light is falling on the mirror normally, means at 90 degree. This length is actually x. If light is falling normally, angle of incidence is 0, and if angle of incidence is 0, angle of reflection is 0, so it is returning back, retracing its path along the same line. But as the question says, if we turn this mirror by a small angle theta, let us say turn this mirror by a small angle theta, what happens? Along with mirror, the normal also turns by same angle theta. Now there is some angle between incident ray and reflected ray, theta. So there will be an equal angle between, now there is some angle between incident ray and normal, in which is theta. So there will be equal angle between reflected ray and normal, which is theta, because of laws of reflection. And now reflected ray will fall at some spot, this. And now you can see it is shifted by a distance y. They are saying it is shifted by a distance y. And this angle is 2 theta. Remember, the theta is very small, as they are saying. My drawing shows the theta is big, but they are not big, they are very small, as suggested in this question. If we apply little geometry, we can say the tan theta, not tan theta, tan 2 theta, this much angle, 2 theta, is equal to y by x. But as theta is very small, the 2 theta 2 is very small, and tan theta can be approximated as just 2 theta equals to y by x. So this gives theta equals y by 2x. So D is your correct choice. Over to next question. Here we have two plane mirrors and they are inclined to each other such that the light incident on first mirror and parallel to the second mirror. Let's dot this much. We have two mirrors like this. Let us say this is the first mirror M1, this is the second mirror M2. And light is falling on first mirror, and this light is actually parallel to the second mirror. And it is finally reflected from the second mirror. Obviously, if we draw a normal, it will be reflected like this. It will fall on the second mirror, and then it will be reflected from the second mirror like this. The question says the finally reflected ray is parallel to the first mirror. So first ray is parallel to second mirror and the final ray is parallel to the first mirror. So if we assume this angle to be theta, this angle too is theta because these two are parallel. The final ray is parallel to first mirror and corresponding angles are equal. And if this angle is theta, this angle too is theta, as these two are corresponding angles because the first ray is parallel to this mirror. Did you notice this is the glancing angle at first mirror, and glancing angle of incident ray is same as glancing angle of reflected ray. So this is also theta. This is law of reflection. And similarly, we have this angle too as theta. Because this is theta, this is also theta, law of reflection. So all these three angles are theta. So the sum of three angles is 3 theta, and this is equal to pi because of triangle's property. So we have theta as pi by 3, that is in degrees we have 60 degree as an answer. So that was a simple question. Let's move forward. Here we have a point source of light S, and it is placed in between a mirror of length d and this line segment. Okay. The source of light is placed at a distance L from the mirror, and this line is at a distance 2L from the mirror, so it is exactly in between. On this line segment, a man walks, and obviously when the man will be in the field of view of image of S, the image of S will be seen by the man. What we have to answer is the distance over which the man can see the image of the light source in the mirror. Okay, so for this, let us first draw the field of view of image. For field of view, what we do, we just draw two extreme rays because they define the field of view. The two extreme rays, and these two extreme rays are reflected like this. And the two extreme rays, the region between two extreme rays is actually the field of view of image. Here only the image is visible. This is the image. So a man walking from below, when enters this point, now he is in the region of field of view, so he is able to see the image. Now as he walks from here to here, he is in the field of view, so he is able to see the image. And when he passes this point, he will not be able to see the image as he goes out of the field of view. Okay. By the property of plane mirrors, we have this length as L, so this length is also L. Now if I take this point as I, this as PQ, let's say the mirror is PQ, and these 2 points are A and B. A and B are the points between which the image is visible to the man. If you see closely, the triangles I, PQ and triangles I, AB, they are similar. Obviously they are similar, they follow law of reflection, and if they are similar, obviously all their dimensions will be in same ratio, or the ratio of every dimension will be same. So if we take the ratio of bases, we have PQ divided by AB. This is the ratio of bases. And let us say the ratio of height. So this smaller triangle's height is L. Considering this as base, its height is L. So we have L as height of the smaller triangle. And height of this bigger triangle, can you see? The height of this bigger triangle is 2L plus L, that is 3L. So we have 3L. Okay. Now if you check, you cancel this L, now you will see that AB is 3 times PQ. And what is PQ? PQ is equal to D. So AB is 3D. So for a distance of 3D, man will be able to see the image of light source. So option A is the correct choice. Now we will study reflection through spherical surfaces. Suppose we have a glass sphere, a hollow glass sphere, and we remove a portion of it. Okay, so that will be a bowl-like structure. Okay, and that is called a spherical mirror if one of its surface is silvered or polished. Okay, so if the inner surface is polished, can you see the inner surface is polished? We also called it is silvered because the polish is of silver. So if we polish it from the inner surface, the outer surface becomes reflecting, and this becomes a convex lens. Convex, not convex lens, convex mirror. And if we polish it from outside, the inner surface will be reflecting, and this is called a concave mirror. Okay. The geometric center of the sphere is still called the geometrical center. So for this also we have geometrical center, and any point from geometrical center on the mirror, like this line, any line, I must say, any line from geometrical center on this mirror, this dotted line or this dotted line may be called as axis of the mirror. Any line, if you draw this line, this also may be called axis of the mirror. This line also an axis of the mirror. This also can be called as axis of the mirror. Okay, and the point where this line cuts the mirror is called pole. And pole is the reference point from where we measure all the required distances. Okay. Let us now understand the concept of paraxial rays and marginal rays. Actually, if you see clearly, then in reflection we have only one law, which is the I equals to R. Okay, but the remaining theory, the object image relationships, the mirror formula, they are all based on paraxial rays, not for marginal rays. So let us understand what are paraxial rays. Suppose we have taken as an example a mirror, a spherical mirror, and here we have an object, and lots of rays are falling on the mirror from object. Okay, the first ray that is incident on the mirror normally retraces its path. The second ray, which is very close to principal axis, incident at this point and returns back in this direction, and it appears to come from this point, right? The third ray returns back in this direction and it appears to come from this point. Ideally, the all rays should have come from or should have appeared to come from a single point, but every ray appears to come from different points. So an observer here will observe image at this point 1. An observer here will observe an image at this point 2. Similarly, observer here will observe image at point 3, and at this observer will observe image at point 4. So this way, a spherical mirror forms infinite number of images for a single point object. And this is actually a defect. This is called spherical aberration. This defect is found in every spherical mirrors, okay. And to reduce this effect, what we do not consider images by the rays which are far from principal axis. We only consider the rays which are very close to principal axis, and these rays which are very close to principal axis are called paraxial rays. And it is believed that all these paraxial rays appear to come from a single point, and that we consider as image. If you use mirror formula, that is 1 by V plus 1 by U equals to 1 by F. This mirror formula is actually derived for paraxial rays only, and this gives you, if you put the value of object distance and focal length of the mirror, this gives you image distance for paraxial rays only. Okay, so that is our theory, and every theory that we study in ray optics is based on mostly paraxial rays. Okay, so let's move a little. Now we will learn how to draw images in spherical mirrors. Always remember, if we are dealing with paraxial rays, a ray parallel to, or incident ray parallel to principal axis will return through focus, and a ray incident through focus will return parallel to principal axis, right? Always remember. Similarly, in convex mirrors, a ray parallel to principal axis returns, and it appears to come from the focus point, and a ray incident towards focus of a convex mirror, okay, is returned parallel to principal axis. Okay, so if you take these rays, it will be easy to draw images. Also, see, if a ray is incident and the ray comes from center of curvature or appears to be passing through center of curvature, in any case, the ray would be normal to the mirror. Because it is passing through center of curvature, so it is a radial line actually. So it is incident normally, and as it incident is normally, the return ray will retrace its path. So the path of incident ray and returning ray is same. Okay. If you take only two rays, then the formation of image is possible. One more thing, as reflection follows law of reflection, the object size and the image size, they may be different. The linear size may be different, but the angular size are always same. If you look the object and image from the pole of the mirror, they will be of equal angular size. Their angle subtended at the pole will be equal because they follow law of reflection. See, as this is the angle of incidence, this is the angle of reflection, they must be equal. So this is object and this is image. HO represents object height, HI represents image height, and they form equal angle at the pole. Okay. So if you want to draw the image diagram for particular mirror, let me show you how we do this. Suppose we have a convex mirror, a principal axis, a focus, and we have an object here. Oh, what we do? We should draw any of the rays passing through focus or parallel to principal axis or passing through center of curvature. So we have center of curvature here and say focus is here. If we put on mirror a ray parallel to principal axis, after reflection it will appear to come from focus, right? And if we incident a light ray passing through center of curvature of the mirror, it will go back and retrace its path. Now, as you know, the intersection point of reflected ray is actually the image. So can you see these two reflected rays, and their intersection point is somewhere here. So we have an image. So we have an object here and an image here. If a real object is placed anywhere in the front side of a convex mirror, the image formed is erect. Erect means it has the same orientation as the object. As object is in upward direction, the image will be in upward direction. It forms between pole and focus, and it is also the small, and you can see the image is virtual. So image is virtual, small or diminished, and erect. Erect means in the same orientation as object. So these are few popular rays. If you use anywhere, you will be able to draw the image diagram. Let me take one more example. Suppose we have now a concave mirror. In case of concave mirror, you have focus on the left side and center of curvature on this side. Okay, on the real side, I must say, or on the reflecting side of the concave mirror. Suppose we have an object here. What we should do? We should draw two popular rays. Say one ray we draw parallel to principal axis, and it will return through focus like this. Right? And if we draw another ray through focus, it will return parallel to principal axis. So an image is formed. And here you can see the image is real. The image is real. It is inverted, and also it is bigger than the object size. So always remember one thing, okay. Remaining diagram you can draw yourself, but let me tell you a few important points. First, if real object forms virtual image or virtual object forms real image, if this is the case, not only in spherical mirrors, in entire optics, the image will always be erect. If image is erect, the magnification would be positive. Right? And if the real object forms real image, as in the case of this diagram, and virtual object somehow forms virtual image, if this is the case, the real object forms real image and virtual object forms virtual image, in this case, image will always be inverted, and magnification would be negative. Positive magnification means erect image, and negative magnification means inverted image. So let us understand few more formulas, okay, of spherical mirrors, and then we can proceed for few solid examples. Say for paraxial rays, all the formula that I am going to discuss are valid only for paraxial rays. The first is, if you know the radius of curvature of the mirror, the half of radius curvature is actually the focal length. Always remember this point. Next is a mirror formula. If you know the object distance, the image distance, and focal length, they all three are related by a single formula, which is 1 upon V plus 1 upon U equals to 1 upon F. Never forget, they are all valid for paraxial rays. Also, if we discuss about magnification, the definition of magnification is height of image, HI, divided by height of object. Height of image divided by height of object. And if you use a little similar triangle property here, you will easily notice that it is equal to, by definition, it is equal to minus V by U, where V is image position with respect to pole and U is object position with respect to pole. Okay. Also, the magnification is defined as M equals F upon F minus U. M equals F upon F minus U. This formula is very useful because here the magnification depends upon U, that is object position only. So if you know only the object position, you can calculate the size of image or the magnification, as there is no use of calculating V first. Okay. There's few more important things. One is sign convention. So actually all these formula are sign sensitive. All object position, image position and focal length of the mirror are sign sensitive. So basically they are not just distances, they are positions. Okay. And how their signs are decided, first you determine or justify or just guess their sign, and then you have to use the values with their respective sign in this formula, then only you are going to get the correct result. So let us understand sign convention. Suppose this is the plane where we have mirror. We may have any kind of mirror, let's say concave or convex, doesn't matter. And the light is being incident from left side. Suppose the light is being incident from the left side. So this is direction of incidence. Direction of incidence. So actually all positions are measured from pole. Remember, all positions are measured from pole, and the positive direction is actually the direction of incident light. Okay. So if some point is here, it will be measured from pole and it will be considered positive. If some point is on the back side, it will be measured on the left side, that is opposite, in the opposite direction of incidence, and it will be measured negative side. Also we have a small convention that if an object or any point is upward, means above the principal axis, it is considered positive, and below the principal axis it is considered negative. So let me take few examples. Suppose we have a concave mirror. If we have a concave mirror, so its focus is somewhere here, the center of curvature is somewhere here. Obviously we will put light on concave mirror like this, so this is positive direction. But if you want to measure the focal length, you will have to measure focal length from pole in negative direction. So for concave mirror, the focal length is negative. Always remember, for concave mirror, focal length is negative. And similarly, you can check for convex mirrors, the focal length will be positive. So let's write this point. For concave and convex, if we check the focal length, for concave it is negative, for convex it is positive. Now let us understand how will be sign of real object and virtual object, and similarly images. Suppose we have an object and it is real. So if we have an object and it is real, take any mirror you want. Say we have taken a concave mirror. If we have an object which is real, obviously the rays incident from the object will be diverging. So object should be somewhere here, means on the reflecting side of the mirror. And if object is somewhere here, if you measure its position from pole, you have to measure the distance or position in opposite direction of incidence. And therefore, for real object you have negative u. Right? And similarly, you can say for virtual object you have positive u. Now, if we think of images, okay. Suppose these rays converge to form image at this point. So if image at reflecting side of the mirror forms, okay, can you see this image is real because the rays are converging and the reflected rays are converging, they form, the intersection point is called real image. And for real image you can see the V is negative because we are measuring it in negative direction according to sign convention. So for real image we have negative V, for virtual image we have positive V. So this is something you should remember. There's one more important point about magnification. We have explained it. Actually, if you have positive magnification, it means erect image, means object and image are formed on the same side of principal axis. And if you have negative magnification, the image is inverted, means the object and image are on the opposite side of principal axis. That is simple meaning of magnification. But if the magnitude of magnification is more than 1, if magnitude of magnification is more than 1, it simply means, yes, if it is more than 1, it simply means HI is more than HO, means we are getting bigger image, and if it is less than 1, HI less than HO, and it means a smaller image. So always remember, if magnitude of magnification is more than 1, we get enlarged or magnified image. And if magnitude of magnification is less than 1, we get diminished or a smaller image. So that's all about spherical mirrors. Let us solve few problems based on this. So here we have an object placed at a distance of 40 centimeter from a concave mirror of focal length 15 centimeter. Okay. So we have a concave mirror of focal length 15 centimeter and an object is placed at a distance 40 centimeter from it. Okay. Now they are saying if object is displaced, but let us first calculate the image position with respect to this position of object. So we'll be using obviously the mirror formula. So for first position, first case, we have formula as 1 over V plus 1 over U, but can you see this object is real and it is on the left side, so the U would be negative, so we have minus 40 and equals to 1 upon F, and as concave mirrors have negative focal length, we can write minus 15 here. This will give you 1 upon V as 1 over 40 minus 1 over 15. Right, and from here you can find the value of V, and I think the value of V would be, let's take LCM as 40, 15, let's take LCM as 120, and if we take LCM as 120, we'll be having 1 over V as 120 and 3 minus, yes, 12. No, not 12, 8. Okay, so we have actually V as 120 by 5, negative of 120 by 5, which is minus 24 centimeter. So the image is at minus 24. We have first image at I1 at minus 24 means on negative side, so we have at image at minus 24. Now in second case, they are saying that object is displaced through a distance of 20 centimeter towards the mirror. So if we displace the object towards the mirror by 20 centimeter, its new object position with respect to pole would be minus 20. And we can apply this formula again, and that will be for second case 1 over V plus 1 over minus 20 equals 1 over minus 15, and this will give you 1 over V as 20 minus 15, so let's take 60 as LCM, right, 60 as LCM, and we will be having what, 3 minus 4, right. So we have V as minus 60. So when object moves here, the image moves backside and the new image position is minus 60. So can you see the image is displaced by 60 minus 24. The displacement of image is actually delta V, which is 60 minus 24, and that's give you 36 centimeter. So obviously the image moves 36 centimeter but away from the mirror. So 36 centimeter away from the mirror is the right choice, right? Okay, let's move to next question. So here they say a particle is oscillating on the x-axis with an amplitude of 2 centimeter about a position x naught equals to 10 centimeter, and we also have a concave mirror of focal length 5 centimeter placed at the origin. So let us understand the problem. We have a concave mirror of focal length 5 centimeter at origin, obviously facing the object, and at x equals to 10 centimeter, we have an object, and this object oscillates left and right, and the amplitude is 2. Amplitude is 2, right? Okay. So if object is changing its position, the image 2 will change its position. The image 2 will do periodic motion as object. Okay. Okay. So the first option says the image executes periodic motion. As object is doing periodic motion, as object is repeating its motion, image must repeat its motion. So the first line is correct. The second line obviously wrong because it says non-periodic. The third line says the turning points of image are asymmetric with respect to image of position at x equals to 10. So as you can see, the object goes from this position symmetrically, 2 centimeter left, 2 centimeter right. So object moves symmetrically. But as the mirror formula says 1 over v plus 1 over u equals to 1 over f, this formula is non-linear. This formula has actually hyperbolic nature. And because of non-linearity or curved nature of this formula, the image will not go symmetrically as object is moving because of non-linearity, right? Only linear functions. If we would have linear functions, then only image could have moved symmetrically. So obviously image will not move symmetrically, image will move non-symmetrically. So this option is definitely correct. Now we have to answer the distance between turning points of oscillations of image. So let us see. As when the object's turning point are here and here, this point is 10 minus 2, that is 8 centimeter from the mirror, and this point is 12 centimeter from the mirror. Let us calculate. Obviously the image's turning point would corresponding to these 2 points, right? So let me calculate. If object is here at A, the image would be, let us see where is image, we'll be using for A 1 over V minus 1 plus 1 over minus 8, as object distance is minus 8 equals to 1 over minus 5. Let us calculate. 1 over V equals 1 over 8 minus 1 over 5 equals, let's take LCM as 40, and we have 5 minus 8 here. So V is actually minus 40 by 3. This is the first turning point of image, and it would correspond to the object position at A. If we calculate the same for B, for object at B, we will be having 1 over V equals, as object is at 12, we will replace 8 by 12. So we will be having 1 by 12 minus 1 by 5. Let's take LCM as 60. So we'll be having 5 minus 12. So we have V as 60 divided by 7, minus 60 divided by 7. The minus sign indicates the position is on the negative side with respect to pole. But as they are simply distances, the difference of these two will give you the difference or the distance between two turning points of images, because these are two turning point of images, right? So that distance they are requiring is actually the difference of these two, and that would be 40 by 3 minus 60 by 7, 40 by 3 minus 60 by 7. So let us calculate this, and you will find 21 as LCM, and the numerator you are going to have get 100. So the difference between turning points of images would be 100 by 21. So fourth option is also correct. So the correct choice of option is, the three statements are right, 1, 3 and 4. So correct choice is A, the 1, 3 and 4. Next question. Here in this question we have an object and it is kept at a distance of 30 centimeter from a concave mirror, and the image is formed at a distance of 10 centimeter from the mirror. Okay. So we have object at 30 centimeter from a concave mirror. Here we have object here, an object at 30 centimeter, and image at 10 centimeter from the mirror. If object is moved with a speed of 9 centimeter per second, the speed with which the image moves at that instant, that we have to tell. So suppose this is u and the image distance is v. As u and v are related by mirror formula, we can write 1 over v plus 1 over u equals to 1 over f. As v and u are nothing but positions of object and image with respect to pole, so their derivatives with time must give you their velocities or speeds. So let us differentiate this formula with respect to time. And if I differentiate this formula with respect to time, we'll be having minus 1 over v square dv by dt. This is the rate of change of image position. So this is the speed of image. Minus 1 over u square du by dt, and equals to, as focal length is constant, the mirror's focal length is constant, that is why the derivative of constant will be 0, and we are getting the dv by dt, that is image speed. You can say it is speed of image equals minus v square by u square, object speed, that is du by dt. Let's put the values. As v square is, v is 30 and v is 10 and u as 30. So we will be having 10 by 30. As we are interested in finding the speed, so minus sign doesn't matter. We have to calculate the magnitude of velocity, and du by dt as 9. So solve this and you will get 1 centimeter per second. So correct answer for image speed is 1 centimeter per second. And let's move over to next problem. Here we are asked, the object is gradually moving away from the focal point of a concave mirror. Okay. So let us assume we have a concave mirror. Say this is its focal point, and object is initially at focus and it is gradually moving away from the mirror from the focal point. So object was initially here. As you know, if object is at focus, the image will be at infinity. So for u equals to f, the image position should be infinity. So if we check this in the diagram, obviously the C and D are wrong, because if u is f, the image should be at infinity and magnification too should be infinity. So here we are getting finite magnification. So these two options are definitely wrong. But here, if we look at this diagram, if u is f, the magnification is appearing to be infinity here, and here also, can you see here, if object distance is f, magnification here is also finite. It says magnification will be infinity or very large for a very low value of object distance. That is wrong. For object distance equals to f, the magnification should be infinity. So only this is your correct choice. We also know that as object is receding from the mirror, when it reaches center of curvature, this distance is actually twice of focal length. The object and image forms at same point. The size of object and image are equal. So magnitude should be 1 at this position. So when object distance is 2f, the magnification here in this graph is 1. So obviously that it is the correct choice, and here we are not getting the correct result. Okay, so that was all. Let's move over to next problem. Here we have a short straight object of height 100 centimeter. Okay, and it lies before a central axis of a spherical mirror whose focal length is 40 centimeter, and the image of object produced by the mirror is of height 25 centimeter. And in the same orientation of the object, means we are getting the erect image. Okay, we are getting the erect image. So actually, suppose here we have mirror, some kind of mirror, and this is principal axis. We have object of size 100 centimeter. As object is real and image is erect, I told you that image will be erect when real object forms virtual image, and virtual image is formed on this side. On this side. So image is of 25 centimeter, image is virtual, and images are smaller. These all things indicate that real objects is smaller virtual image. This can be formed only by a convex mirror. This can be formed only by a convex mirror, because concave mirror, when they form virtual image, the virtual image is bigger in size. Only convex mirror form virtual image of real object, and that too in a smaller size. So obviously the image is virtual. That is obviously clear, because the erect image can only be formed by real object when image is virtual. Okay, so image is virtual, and on the opposite side of convex mirror, bilkul, right? So D is your correct choice. Now we will study what is refraction. Actually, when light traveling in a medium enters some other medium, it is observed the path of ray changes. Like if a light is traveling in medium 1, this is medium 1, and it enters a different medium, what we see, its path is changed. Sometimes it bends towards normal, or sometimes it bends away from the normal. Means its path is changed. There is some deviation in path, and this event is called refraction. The word refraction is from fracture. Can you see? Fraction. So it is from fracture, means what? Breaking. So the path of light ray is breaking actually, that is, we say it refraction. And actually the optical property of medium that is responsible for this refraction or this bending of light is called index of refraction or refractive index. Let us understand what is index of refraction or refractive index. We represent this quantity by n or sometimes mu. Okay, let us revise a small concept from electromagnetic field theory. I think you remember the speed of light in vacuum is given by 1 over square root of mu naught and epsilon naught. This is speed of light in vacuum. The V stands for vacuum, where mu naught and epsilon naught are actually permeability and permittivity of free space. This is magnetic property, this is electrical property, and as you know, the light is electromagnetic. It depends upon both the magnetic property and the electrical property. If we want to know the speed of light in some medium, in medium the speed of light would be 1 over square root of mu times epsilon, where mu is permeability of that medium and epsilon is actually permittivity of that medium. So actually some mediums refractive index mu is defined as n, or mu is defined as speed of light in vacuum divided by speed of light in that medium. If you put these two values here, you will find square root of mu epsilon naught, epsilon divided by mu naught epsilon naught. I think you remember from electrostatics that mu by mu naught is actually called relative permeability and epsilon by epsilon naught is called relative permittivity. So actually the refractive index is square root of multiplication of relative permeability and relative permittivity of the medium. This is what the refractive index is. And the basic is it is equal to the ratio of speed of light in vacuum divided by speed of light in medium. When light from one medium enters some other medium, the speed is definitely changed. Okay, the speed is changed means the light moves either slower or faster in some other medium. But if we are comparing the speed of light in vacuum, so the speed of light is fastest in vacuum. And when it enters any other medium, the speed gets always slower. So that is why we say the refractive index of any medium, other than vacuum or air is always more than 1. The refractive index of medium is more than 1 and it is equal to 1 only in the case of vacuum or what? Air. Also the frequency remains unchanged. Okay, if the light has some frequency here, it will have same frequency here. The color remains same color here. But the wavelength changes. If the light has a wavelength lambda here the wavelength becomes lambda dash, but means we get some different wavelength because the speed is changing and speed equals to frequency times lambda. So if speed increases, lambda increases. If speed decreases, lambda decreases in equal proportion. So that is because of refractive index or index of refraction of the medium. Now let us understand what are laws of refraction. Okay. So let us take example of a refraction. Suppose we have one medium, this medium, and here the index of refraction is n1. Let me write it as mu1, and below this line we have refractive index as mu2. And a light traveling in medium 1 and it is at angle of theta 1 from normal. So angle of incidence is theta 1 and this light enters the other medium, okay, and in other medium the angle with normal is theta 2, right. So actually the refractive index and theta 1 and theta 2 are related by a law, and that too is called Snell's law or law of refraction. And what we observe is, we observe mu1 sin theta 1 equals to mu2 sin theta 2. That is called Snell's law or law of refraction. Okay. So remember one point, as the multiplication of mu and sin theta is constant, mu1 sin theta 1 equals to mu2 sin theta 2. As mu increases, the theta will decrease. As mu increases, theta decreases. And if mu decreases, theta increases. So suppose the mu2 is bigger than mu1. If mu2 is bigger than mu1, the theta 2 would be smaller than theta 1 because the product has to remain constant. Product of mu and sin theta has to remain constant. So if mu2 is bigger, theta 2 is smaller, and we say the light bends towards normal. In fact, if refractive index of a medium is large, like here, the refractive index mu2 is large than mu1, the second medium is called denser medium as compared to the first, and the first is called rarer as compared to second. Okay. So actually when light ray enters from a rarer medium to denser medium, it bends towards normal, and in opposite case it bends from away from normal. So first we will study the plane surface refraction. What is plane surface refraction? And I'll tell you a very simple strategy for solving plane surface refraction questions. So just follow this. Suppose we have a plane surface, and this surface separates two medium, one on left side and one on the right side. The left side medium has refractive index n1, and the right side medium has refractive index n2. So when a light ray from n1 goes from this side to this side, it is refracted by this plane surface. The boundary is plane. The boundary dividing these two media is plane. So when light ray when light ray enters from this surface, so from this medium to this medium, it is being refracted by this plane surface. Okay, so we can call this as pole and this as axis, and let us assume the object distance from pole is u, right? And we have to know, suppose we have to know image distance. So always for paraxial rays, the formula here between u and v is equal to n2 by v equals n1 by u. n2 by v equals n1 by u. Using this formula, you can solve any problem of plane surface refraction. But remember one thing. The first important point here is, as the equation says, v and u will always have same sign. Either both will be positive or both will be negative. It means they are on same side. They will always be on same side of the plane refracting surface. Either they both will be on this side or they both will be on this side, because the v and u should have same sign. So if they are on the same side, obviously if object is real, the image should be virtual, and if image is real, the object is virtual. So only two cases are possible: real object, virtual image; virtual object, real image. Because real objects, real image are formed when they are on opposite sides of the surface. You should also remember one point. Sometimes many students remember it like this, that n1 is the medium where we have object and n2 is the medium where we have image. This is wrong, because here we see object and image on the same side. So we should remember it like this: n1 is the medium where we have incident light. So n1 is the medium of incident light. Obviously, if we put some incident light on the refracting surface, we see incident light is in n1. So n1 is always the medium of incident light and n2 the medium of refracted light. So obviously after refraction, the light goes in this medium like this. And the refracted light, if appears to come from this point, this is your image. Okay, and the object distance and image distance, always remember, are related by this formula. Okay, suppose we take a very simple and very apt example for this. We have a river or a bucket filled with water, and we have an object at the bottom. As this is the surface that separates water from air, so it is the plane refracting surface, and object distance from plane refracting surface can be called as u, and say it is equal to h. When light ray is refracted here, okay, there is one more thing. We derive this formula for paraxial rays, and for paraxial rays, all the rays will be very close to axis. And if all the rays are very close to axis, these angles I and R are actually very small. Consider this ray very close to this axis. You will yourself will notice an I and R should be small. Actually, I have drawn them bigger for clear visibility, but actually they are very small. So if I and R are very small, we say here that incidence is near normal. So we derive everything for paraxial ray, and paraxial ray and near normal incidence are almost same. So it is for near normal incidence. And if we wish to know what is the image distance V, let us apply the formula. N2 by V. What is N2? Can you see the refracted light is in air? As the refracted light is in air, we have N2 of air as 1 divided by V equals to N1 by V. U, what is N1? The ray where incident light is, the medium is water. So we have water's refractive index is, let's say, mu, and divided by U, and the value of U is H. So we get V as H by mu. We get V as H by mu. As H is more than 1, we here get the image distance from the refracting surface as is smaller than U. And when you observe this image from above, like this tiny object appears here. So this image distance is also called apparent depth. It is called apparent depth, right? Now we will study what is the shift caused by a transparent glass slab. What is a glass slab? Glass slab is simply a transparent medium bounded by two plane surfaces. Only these two surfaces are optically important. So we ignore these surfaces because refraction is not taking place at these surfaces. The refraction is taking at these two surfaces. So only these two surfaces are important. And we say the glass slab is actually a transparent medium bounded by two plane surfaces. Suppose the two plane surfaces are separated by a distance t, and the refractive index is mu. And if we have an object here, the light from object, say one light goes like this and one light goes like this. As outside we have assumed air, inside we have assumed a medium. So light will bend toward normal, and then when it comes again in the same medium, it again becomes parallel to the incident ray. And if you extend the final ray backwards, they meet at this point. So this is actually the image position or the apparent position of object when you observe from here. So what we see, that apparent position of object is shifted in the direction of incident light. So shifting is in the direction of incident light, and this shifting, if you calculate from the formula that I just gave you, you find this shifting delta S. I am skipping the derivation part. So the shifting delta S will be equal to T times 1 minus 1 by mu. So this is shift. Always remember, this shift is not dependent upon the distance of object and slab. So if you move object, the image will move by equal amount in equal direction because the shift is not dependent upon object position. It depends only upon the refractive index of slab and on the thickness of the slab, right? Okay. We also have lateral shift. If you even look in the old diagram, okay, if you extend the initial path of light and you see the final path of light, they both are parallel. So there is no angular deviation of ray when it passes through the slab, but the ray shifts by a little distance, and this distance is called lateral shift. Remember, this distance is called lateral shift. Okay, so I'm taking this example. Suppose we have a ray incident at angle I on the slab. The thickness of slab is T, right? And it is refracted at an angle R here. And when it goes outside, it again becomes at angle I from the normal. But if you extend the initial ray and final ray, they both are shifted by a distance D. So here we have lateral shift as D. If the thickness of glass slab is T angle of incident I and angle of refraction as R, just try some geometry here and very easily you can calculate D. And let me write directly the formula. The D comes out to be T times sine I minus R divided by cos R. This is the formula for lateral shift. We should also know what will be lateral shift. If the incidence is near normal. So we discuss a special case of near normal incidence. For near normal incidence, light ray would be almost perpendicular to the slab and I and R would be very small angles. So for very small angle, I think you remember, if angle is very small, sine of that small angle is almost equal to theta and cos of that angle is almost equal to 1. So if I and R are very small, you can write D as T times I minus R divided by cos R, which is 1. So it is the formula for lateral shift. Remember, put I and R not in degrees, you should put them in radians. Okay. But as if you use Snell's law here, you can write sine I, but as I is small, just write only I. If I use Snell's law, sine I equals to, the refractive index is say mu, so sine I equals to mu sine R, but as I and R both are small, I can replace sine I and sine R as simply I and R. So we have R as I by mu. So if you put it here, you get T times I minus I by mu. So we have I times T times 1 minus 1 by mu. So as I just told you that T times 1 minus 1 by mu is the normal shift. So if you multiply normal shift by a small angle of incidence, if any, then it will give you the lateral shift. So normal shift and lateral shift are related. Okay. But only in the case of normal incidence, that you should remember. Here we are given that if we have a tiny air bubble inside a glass slab, see, we have a glass slab and we have a tiny air bubble in it, and when it is viewed from one side, it appears to be 5 centimeter deep. So when we see it from here, it appears to be 5 centimeter deep. See, it appears to be 5 centimeter deep, it means we are looking at apparent depth. Okay. So the 5 centimeter that we are looking is apparent depth. Let the real depth is A. So as the apparent depth 5 centimeter is A by mu, we have A as 5 times mu, and as mu is 1.5, we have A as 7.5. But when we look the same bubble from this side, it appears to be 3 centimeter deep. So if the real depth is B from the right side, the apparent depth is only 3. So we can write the apparent depth 3 as the real depth B divided by mu 1.5. So we have B as 4.5. So if the depth of real depth of bubble from this side is A and from this side is B, the total thickness of slab would be A plus B obviously, and if you add A plus B, you get the 12 as correct choice. Okay, so let's move over to next question. Here in this question we have a vessel of depth 2h. We have a vessel of depth 2h, H and H, right? And actually a liquid is filled up to the half of height, and that refractive index of the liquid is 2 root 2, and above the first liquid we have a second liquid of refractive index root 2. these two liquids do not mix with each other, so you can say they will always remain as shown in the figure. Now they are asking us what is the apparent depth of inner surface of the vessel. So suppose we have this inner surface, and above this inner surface we have two transparent slabs, and the two transparent slabs collectively shift this lower surface or the bottom surface upward. Means because if you are looking at this from above, the incident light is in this direction, and you know the normal shift is in the direction of incident light, so this will be shifted upward twice with two surfaces. As the shift is given by, let us calculate the total shift. The total shift will be equal to shift by first slab and plus shift by second slab. As the formula for shift is thickness times 1 minus 1 over mu, so we have thickness as h, 1 minus 1 over 2 root 2. This is shift by first slab plus h times 1 minus 1 over root 2. This is shift for second slab. If you add these two, you will get 2h minus actually 1.5h divided by root 2. This is the upward shift. So if the bottom is shifted upward, its real depth will be the total height minus shift. So apparent depth you can write as h apparent can be written as 2h minus delta h. Okay, oh sorry, 2h minus the delta shift. So if you calculate this, you minus 2h minus this, so you have the h apparent as 1.5 is 3 by 2, so we have 3h by 2 root 2. As none of the answer is matching, let us rationalize it and multiply root 2 from in numerator and denominator, and then you will see B is your correct choice. So let's move over to next problem. Now we will study total internal reflection. This is really an amazing phenomenon that occurs in refraction. Let us understand when it occurs. Suppose we have a boundary that separates two media. The one media has index of refraction n1 and the other media has index of refraction n2. Let's say n1 is more than n2. Means the light is going from n1 into n2. So light is going from denser medium into rarer medium. Remember, the TIR or total internal reflection occurs only if the light travels from denser to rarer medium. So if light is traveling from denser medium to rarer medium, obviously the light ray bends away from normal and the value R is more than I. If you gradually increase the angle of incidence, the R also increases, but as R is bigger than I, the R reaches the value 90 degree first. So if we gradually increase the angle of incidence and we reach a situation where the angle I is a spatial angle I for which the angle of refraction R is nearly or almost 90 degree. We say this spatial angle I as critical angle theta c. So what we have learned? It says when light ray travels from denser medium into rarer medium, it bends away from the normal. It bends away from the normal. And if angle of incidence is increased, the angle of refraction also increases. And a particular value of angle of incidence at which when the angle of refraction becomes 90 degree, this angle of incidence in denser medium is called critical angle. So we have theta c as critical angle. What is the importance of critical angle? Let us understand. If angle of incidence is smaller than critical angle or just equal to critical angle, we say light is refracted into the rarer medium. So refraction occurs. Refraction occurs. But what if I is more than critical angle? If I is more than critical angle, refraction cannot occur because the R cannot be more than 90 degree. So we do not get any ray in second medium or rarer medium. We have no ray in rarer medium, and the percentage of light reflected becomes 100%. 100% light is reflected back into the same medium following law of reflection. So we get reflection. We get reflection. But as the percentage of reflection is 100%, okay, as the percentage of reflection is 100%, we call it total internal reflection. Okay, and now let us understand how we calculate theta c. How we calculate theta c. Just look at this diagram. Here we have n1 as refractive index. Here we have n2 as refractive index. n1 is bigger or n2 is smaller. So if we apply Snell's law here, we get n1 sine theta c, because angle of incidence is theta c, equals n2 sine 90, because angle of refraction is 90. Sine 90 is 1. So you get theta c or angle of refraction as sine inverse n2 by n1, n2 by n1, or you can also call it as theta c as sine inverse 1 by n, where n is refractive index of 1 with respect to, that is refractive index of denser medium with respect to rarer medium, refractive index of denser medium with respect to rarer medium. So that is the definition of critical angle. And always remember, when angle of incidence is more than critical angle in denser medium, light do not refracts. It is completely reflected back into the initial medium, and if angle of incidence is less than critical angle, it goes into the other medium. This is again a diagram showing the same phenomenon. Suppose we have a light source here in this medium n1, and here n1 is more than n2, n1 is more than n2. If we take a light ray going normally, obviously it will refract. If we take a light ray like this, obviously it will refract, but as we are going towards light on the right hand side, their angle of incidence is increasing. Okay, try imagining large number of lights, but as you go on right side, the angle of incidence will increase, because here angle of incidence is 0, here it is theta 1, it will be theta 2 again, and when the angle of incidence becomes theta c, when the angle of incidence becomes theta c, the light is refracted but at 90 degree, and if you think of any other ray with angle of incidence more than theta c, it will totally be reflected. It will totally be reflected, right? So we get refraction up to this distance only. We get refraction up to this distance only r, right? If you draw the same diagram on the left side, you will get refraction up to a distance r only. If you draw the same diagram in this direction towards you, you will again see refraction up to a distance r. Means if you just draw a circle of radius r above this point source of light, we get refraction through that circle only. We get refraction through that circle only, or you can say the light is refracted into rarer medium through that circle only, and that is why that circle is called circle of illumination. Here, a spatial light ray which falls at critical angle C. This light is refracted at 90 degree. Similarly, here also, the light at theta C is refracted. So you can imagine a cone of half angle theta C, and the light inside this cone is refracted into the rarer medium. So you can imagine a circle here through which the light is being refracted, and all other light will be trapped inside the medium. Okay, all other light will be trapped inside the medium. If we wish to find the radius of this circle, that calculation is simple. See, if the height of source is h and the radius of the circle is r, okay, as this angle is theta c, this angle too will be theta c, as alternate angles are equal. We can write, or let us assume we outside we have air and inside we have a medium n. So as by the definition of critical angle, sin theta c equals 1 by n. Sin theta c equals 1 by n, and we can write tan theta c as r by h. So we get radius as h tan theta c. But if you know sin theta c, calculation of tan theta c is not difficult. We can always assume a triangle where this angle is theta c, this is 1, this is n, so this would be root of n square minus 1. So tan theta c becomes 1 over root of n square minus 1. Okay. If light is being emitted, only a fraction of light is obtained in this side. Only a fraction of light is obtained in above medium, and remaining light is trapped inside the denser medium. If you want to calculate that fraction of light being emitted, we will have to use the concept of solid angle, but let me write you straight the formula. The fraction of light emitted in air equals 1 minus cos theta c, where theta c is angle of incidence, the critical angle actually, and divided by 2. This is the fraction of light emitted. And if you wish to know what is the percentage of light emitted, just multiply this fraction by 100. That will be the percentage of light emitted. Okay. So let us solve few problems based on this. Here it says, in total internal reflection, when the angle of incidence is equal to critical angle, for the pair of media, what will be angle of refraction? So you already know, when angle of incidence is critical angle, the angle of refraction is always 90 degree. So obviously D is your perfect choice. This is the most simplest one. Next we have the critical angle of medium. We have to know the critical angle of the medium for a specific wavelength. And for that wavelength, the medium has relative permittivity 3 and relative permeability 4 by 3. I think you remember the refractive index is given by square root of relative permittivity times relative permeability. If you put the values here, you have epsilon r and epsilon mu r as 3 times 4 by 3. So we have 3 got cancelled, and the refractive index is simply 2. And if refractive index is 2, the sine theta c, which is equal to 1 by n, it becomes 1 by 2, and if it is 1 by 2, obviously the theta c is pi by 6 or 30 degree. So B is your correct choice. Next. Now they say there is a small source of light at some depth below the surface of water of refractive index 4 by 3 in a tank of large cross section area, and neglecting any reflection from the bottom and absorption by water, what is the percentage of light that emerges out of the sphere? As I told you few minutes back, that percentage of light, the fraction of light or the percentage of light equals 1 minus cos theta c divided by 2. This is the fraction emerging multiplied by 100. So we have to just know the value of cos theta c. As sin theta c, let me tell you, as sin theta c is equal to 1 by n, so it will be 3 by 4. You can easily calculate the value of cos theta c. And if you take a triangle like this, where sin theta c is 3 by 4, so this is 3 by 4. This is theta c. You can notice that this will be root 7, and cos theta c would be equal to root 7 by 4. Cos theta c is root 7 by 4. You put the cos theta c, the value of cos theta c as root 7 by 4 here, and calculate this, and you will get approximately the 17% as the correct answer. So correct answer is 17%. Now we will learn another example for plane surface refraction, and it is actually a prism. So what is a prism? Prism is actually again a transparent medium, and it is bounded by two surfaces at some angle. So if there are two surfaces and they are bounding a transparent medium of, say, refractive index n, and the two surfaces are at some angle A, we say this is structure as a prism. These two surfaces are important because refraction is taking at these surfaces place. Okay, so the angle between these two surfaces is called angle of prism, angle of prism, or sometimes it is also called refractory angle. Refractory angle. Let us understand of this phenomenon. Suppose the light ray enters this prism, and at the entrance it makes angle I with normal. When this light ray enters this medium, we have angle of refraction as R. Let us call this angle as R1. Then this light enters or is incident on the second boundary, and where angle of incidence can be assumed to be R1, and when it emerges on the initial medium, let angle with normal is E. So we call this I as angle of incidence, this angle E as angle of emergence. If you just flip the direction of the light, the arrows to the left, the geometry doesn't change, every angle will be same. But at that time, this would be angle of incidence, this would be angle of emergence, but the value will remain I and the value will be E. So you can say I and E are interchangeable. If you are getting angle of emergence as E with angle of incidence as I, you will get angle of emergence as I when angle of incidence becomes E. That is simple reciprocity of light. Let us, it is actually R2. Okay, R2. See, the first deviation with light is delta 1. Okay, and delta 1 can be written as I minus R1, and delta 2, the second deviation, can be written as E minus R2. So if you want to calculate the net deviation in the light's path, this is the net deviation, delta. The delta can be written as the sum of delta 1 plus delta 2, that would be I plus E minus R1 plus R2. Okay. What is R1 plus R2? That you can see very easily from this triangle, the triangle formed by two surfaces and the refracted ray inside the medium. From this triangle, properties of this triangle, you can easily check that the sum R1 plus R2 is equal to A. So the deviation becomes I plus E minus A. These are the two important formula. Also I and R1 and E and R2 are related by Snell's law. You can always write sin I equals n sin R1, sin E equals n sin R2. So these are the basic formula of a prism. We can write sin I equals n sin R1 and sin E as n sin R2. First important thing. The second is R1 plus R2 equals A, and third, the deviation is I plus E minus A. Okay. Let us see what this question says. This says the refractive index of the medium of a prism is √2. The angle of prism is 30, and one of the two refracting surfaces of prism is made a mirror inward. So we have a prism like this. Angle is 30, refractive index is √2, and see, this surface is made a mirror by polishing, by silver coating. Now they say a beam of monochromatic light entering the prism from the other face and retraces its path. So we have a beam of light or light ray here, and it goes into the prism and finally it retraces its path. So retracing occurs if at mirror we get normal incidence. Obviously it means when the light ray is incident on the mirror, it is normal to the mirror. Okay, let me just draw the normal. Let us say this angle is I, and I think yes, we want to know what is the angle of incidence I. Okay. As this angle is 30, this is 90. Obviously this angle is 30, and if this is 30, this is 60. So angle of refraction here is 60. Okay, angle of refraction is 60. The refractive index is √2. Let us calculate I. No. It is not 60. By properties of triangle, this angle is 60. Yes, this is 30, this is 60. So angle of refraction would be 30. Angle of refraction would be 30. You please check. So I can write according to Snell's law, sin I equals n, that is √2, and sin R, which is sin 30. So I can write sin I as √2 multiplied by 1 by 2, which becomes 1 by √2. So I becomes 45. So C is your correct choice. Okay. So here in this question we are asked what is the angle of emergence from the prism if refractive index of the prism is √3. So we are given a prism of this angle as 60, this as 90. So this automatically becomes 30, and light is being incident on this hypotenuse normally. So it will go straight like this, and it will be again incident on this vertical flat surface. If you look at the little geometry, if this angle is 30, this will be 60, and if this is 60, this automatically becomes 30. And when light ray emerges out, let's say the angle of emergence is E. Now if we apply sine rule or Snell's law, in fact Snell's law, I must say, I can write Sine E equals mu, which is root 3, and sine 30. And what is sine 30? 1 by 2. Actually, mu is root 3. So we have sine E as root 3 by 2. And if sine E is root 3 by 2, E becomes 60 degree automatically. So we have A as correct choice. Okay. So let us move ahead. So it is a very important question for theoretical reasons. So let us understand this. It says, what is the angle of incidence? What is the angle of incidence? They are calling this angle of incidence as IG, for which the emergent angle is almost 90 degree. Or if the emergent angle is 90 degree, we say the light ray emerges from the surface grazingly, because the light ray grazes the second surface. So here we can say that E equals 90 degree, and we want to know what is the value IG. Okay, so let us solve this question. I think it is a common fact, you remember this, that if angle of refraction in rarer medium is 90, the angle in denser medium becomes theta c, right? And as the sum of these two angles R1 and R2, we call these angles as R1 and R2, and sum of R1 plus R2 is actually A. So if the sum of these two angles is A, this becomes A minus theta c. If refractive index is mu, I can apply sine rule on this surface. I can apply sine rule on this surface, and applying sine rule, it gives us sine Ig equals mu times sine A minus theta c. So from here, Ig becomes sine inverse mu sine A, and I think you remember the sine theta is 1 by mu. I think you remember sine theta is 1 by mu. So theta c becomes sine inverse 1 upon mu. So this is the value of Ig, and if Ig or angle of incidence is this much value, the emergent ray will be grazingly emerge. Okay. So let us analyze it a little bit more. Suppose you decrease the angle of incidence as compared to Ig. If we decrease the angle of incidence, this angle will be decreased, this angle will reduced, and if this angle is decreased, this angle will automatically increase, as their sum is constant and equals to A. So if this is decreased, it will increase, and if this angle increases more than critical angle, the light ray will be reflected back in the same medium and it will suffer TIR. So always remember, if we decrease angle with respect to Ig, the light ray suffers TIR at second surface. So you can say for I in between 0 and Ig, what happens? We see TIR at second phase. We see TIR at second phase, right? And if I is more than or equal to Ig, or you can say if I is more than or equal to Ig and less than 90 degree, if it is less than 90 degree, what happens? If Ig is more than or equal to Ig and less than 90 degree, means I is bigger than Ig. See, if I is bigger than Ig, this angle will be increased. If this angle increases, what happens? This angle will decrease as the sum is constant, and if this is decreased, the angle here is less than critical angle. And if angle is less than critical angle, the light ray will emerge out at some value of angle of emergence. So we see emergence if I is bigger than the value Ig. So we see refraction at second phase. We see refraction at second phase. You must also notice that the real value of Ig is only possible, real value of Ig is possible if the angle A, the angle of prism A, is more than theta C and less than 2 theta C. I think this argument or this statement needs some explanation. That is why I am taking a next question related to this. So let us understand a little more. But remember, if Ig exists, if you get the value Ig, for angle of incidence less than Ig, for angle of incidence less than Ig, we face TIR, the light ray faces TIR at second phase. And if I is more than Ig, less than 90 degree, the refraction occurs, means refraction occurs at both surfaces. Let us understand the last point I made. So suppose here we have to show that if A is less than theta C, if A is less than theta C, the ray at second surface always emerges. Always emerges, means for any value of I, the ray at second phase always emerges, and if A is more than 2 theta C, the ray at second surface always undergoes TIR. Let us understand. Suppose we have a prism and the angle A is less than theta C. Let us say a light ray is trying to cross this like this. Okay. So here we have two angles R1 and R2. As R1 plus R2 equals A and A is less than theta C, so R1 and R2 both will be less than theta C because their sum is less than theta C. If their sum is less than theta C, how can any one of them be more than theta C? So obviously R2, we can make a point here that R2 is less than theta C. And if R2 is clearly less than theta C, the TIR cannot take place and light ray will definitely emerge. So this proves this point that if A is less than theta C, the light ray definitely emerges. There is always refraction, the TIR cannot take place. Okay. And let us make a second point. If angle of prism A is more than 2 theta C, if angle of prism A is more than 2 theta C, R1 plus R2 is actually more than 2 theta C. Now suppose a light ray tries to enter the prism. If it is entering into denser medium, if prism has denser material as compared to outside medium, mu is more than 1. Okay. For any value of angle I, the R1 would definitely be less than theta C. The reason is because if I is 90, R1 equals theta C. That is a common fact. If I is 90, then R1 is theta C. So if I is less than 90, R1 is definitely less than theta C. So if you look at this and you make a point that R1 is less than theta C. So if R1 is less than theta C and this sum is more than 2 theta C, definitely R2 would be more than theta C. And if R2, the angle here at second phase, is more than theta C, this is a sufficient condition, this is a very necessary condition for TIR to take place at second phase. So if R2 is more than theta C, at second phase, the TIR takes place. So you should remember this important point in your mind that if A is less than theta C, all rays will emerge out. And if A is more than 2 theta C, no rays emerges out, means all rays at any angle suffers TIR at second phase, right? So therefore, it becomes very logical that when A is between theta C and 2 theta C, then only an angle of incidence Ig exists or real root exists, where for smaller angles you get emergence. Oh, sorry, TIR for smaller angles. For angles smaller than IG, you get TIR at second phase, and for bigger angles, you get emergence at second phase. So I think I made my point. This is again a question, and it says that the monochromatic light is incident on a glass prism of angle A. The refractive index of the material is mu. Now they say a ray is incident at angle theta on the face, and AB would get transmitted through the face. Would get transmitted through the face of the prism provided. So you know that, as we have discussed here, if I is more than IG, see, if angle of incidence is more than IG, refraction will definitely take place. Okay. So if we take this advantage, I think you remember the value of IG is this. We just proved it. So value of IG is this. And if angle theta is more than this value, the refraction at second phase will definitely take place. So we have C as correct choice. Okay. So let's move to next concept. As we now know, the role of prism is to deviate the light. Okay. So I am taking a prism where the angle of prism is A and it is more than theta C and less than 2 theta C. And in this range, if angle of prism is in this range, there exists an incident angle IG, and if angle of incidence is IG, the ray suffers grazing emergence at second phase, right? And if I is between IG and 90 degree, the ray always emerges out of the prism. So we are considering a case where the ray always emerges at second phase, means ray after passing through prism, it always emerges at second phase, and where we see the deviation is equal to, actually deviation is I plus E minus A. So as the angle of emergence depends upon angle of incidence through Snell's law, we can say the deviation is a function of angle of incidence. You vary angle of incidence and the deviation will also vary. If we make an experiment and let the light pass through a prism, and as refraction only takes place when I is between IG and 90, let us gradually vary the angle of incidence from IG and 90. And what we observe? We observe that the deviation is maximum when angle of incidence is IG or 90. Remember this point, when angle of incidence is either IG or 90, the deviation is maximum. Experimentally, we find the deviation is maximum. And in between, when IG varies from here to here, the deviation first decreases and then gradually increases. So remember this point, the condition for maximum deviation is I equals IG or 90. If I is IG, E will be 90, angle of emergence will be 90, and if I is 90, angle of emergence will be equal to IG, because light follows symmetric path, right? If you just flip the direction of light ray. Okay. So what we can say here is that if I is IG or 90, maximum deviation takes place, or E is IG or 90, maximum deviation take place. So we must say either of E or I must be equal to IG or 90. The second one automatically becomes, if first becomes IG, the second becomes 90. If first becomes 90, second becomes IG. Okay. So remember this point, any one of I or E must be either IG or 90. And what we observe when, this is a fundamental, you can say experimental result, that when the angle of incidence and angle of emergence are equal, or you can say the light passes through prism all very symmetrically, and if light passes through prism symmetrically, I and E would be equal, R1 and R2 would be equal, and then we see the deviation is minimum. So condition for minimum deviation is I equals to E. If I equals to E, this is the main condition, and from this condition we can also write R1 equals to R2. As the sum R1 and as the sum of R1 and R2 is A, and if they both are equal, they both will be A by 2. Okay, so using sine rule, we can write sine I equals mu sine R1. Sine I equals to mu sine R1 at first phase. But see, if I and E are equal, we can write the delta as minimum, because we are looking here at when I and E are equal, the deviation is minimum. So using this equation, we can write delta minimum equals I and E are same, so I can write 2I minus A, so I becomes delta minimum plus A by 2, and R1 becomes A by 2. Putting these values in the Snell's law here, we get mu as sine I by sine R1, so we get mu as sine I. What is I equal to? Delta minimum plus A by 2 and divided by sine R1 as sine A by 2. So this is the relation that relates prism angle, refractive index, and minimum angle of deviation. So let us solve few problems based on this. Here we have a monochromatic light incident at a certain angle on an equilateral triangular prism, and it suffers minimum deviation. If the refractive index of the material is √3, then what is angle of incidence? Okay, let us solve. Say this is the equilateral prism. This is angle 60 degree. And as light ray suffers minimum deviation, it must pass through the prism symmetrically, like this. Symmetrically. Okay. Remember this point. If your prism is an equilateral cross section, if your prism has equilateral or isosceles cross section, always the ray inside the prism will be parallel to the base in case of minimum deviation. Okay, so here we have to know the angle I. The R1 becomes A by 2, that is 30 degree, and refractive index of the prism is known. Let us apply Snell's law. We have sine I equals √3 times sine R, and what is sine R1? Sine R1 is sine 30, and which is 1 by 2. So we have sine I as √3 by 2. This gives you I equals to 60 degree. So C is your correct choice. Over to next question. Here they say angle of incidence of a prism is 45, angle of prism is 60, and ray suffers minimum deviation. Okay, then the angle of maximum deviation and refractive index of the material are. No, the angle of minimum deviation. So we have to know the angle of minimum deviation and refractive index of the material. So as we already know, minimum deviation equals, in case of minimum deviation, I and E are equal. So I can write I plus E as simply 2I and minus A. As I equals 45 degree and angle of prism is 60, we can write 2 into 45, that is 90, minus 60. So angle of minimum deviation becomes 30 degree. So 30 degree is the right answer for angle of minimum deviation. So either B or D is correct. Now if we apply Snell's law at first phase, I can write sine I, so sine 45, as I is 45 degree, equals mu. So what is mu? Let us write value of mu as mu. And sine R, as you know, R is equals to A by 2. We can write sine R as A by 2. And what is A by 2? 30 degree. So we have mu as, just put the value, sine 45 as 1 by root 2, sine 30 as 1 by 2. So we get mu as root 2. So B is your correct choice. You can mark this B directly because always for a material other than vacuum or air, we have refractive index more than 1. And as this is less than 1, obviously B makes perfect choice. In this question, the question says the refractive angle of a prism is A and refractive index is given in terms of A as cot theta A by 2. What is angle of minimum deviation? Okay, so let us solve it. As the angle of deviation is minimum, you can write R, all R1, R2 are A by 2. Okay, so if we apply the Snell's law at first phase, I can write sine I, let us the angle I as angle of incidence, sine I equals the refractive index, which is cot A by 2, cot A by 2, and multiplied by sine R1. So R1 is A by 2, so we have sine A by 2. If you write cot A by 2 as cos A by 2 divided by sine A by 2, we have sine I equals cos A by 2. Now this cos A by 2 in terms of sine can be written as sine 90 minus A by 2, because sine 90 minus A by 2 is equals to cos A by 2. And by comparison, we can write I as 90 minus A by 2. Now, as you know, the minimum deviation, as deviation as I plus E minus A, but in case of minimum deviation, I and E are equal. So minimum deviation is actually 2I minus A. So if we write 2I here as, make it twice, we have 180 minus A and minus A. It becomes 180 minus 2A. So D is your perfect choice. So now we will study the refraction through a thin prism. What is a thin prism? We call the prism thin if angle A is less than 10 degree. If angle is smaller, we call it a thin prism. Okay, and we are considering near normal incidence, means light ray also the crossing the prism almost normally. Okay, so in this case, if light ray is crossing the prism almost normally, all angles I, R, R1, R dash, or you can say I, E, R1, R2, all will be very small angles. So I can write I, E, R1 and R2, all are small angles. And if they are small angles, sine of a small angle can be written as sine theta as only theta. So if you apply Snell's law at first phase, I can write I equals mu R1, and at second phase I can write mu R2 as E, right? Now as you know, the deviation is equal to I plus E minus A. Let's add I plus E, and if you add I plus E, you will get mu times R1 plus R2 minus A. And as for any prism, we have R1 plus R2 also equals to A. So it becomes mu times A minus A. So if we take A common, we get mu minus 1. So remember this point. For near normal incidence, in case of a thin prism, the deviation is almost constant. It is not dependent upon the angle of incidence, but yes, the angle of incidence should be small or in the range of say less than 10 degree. So it is independent of angle of incidence. and all rays falling at small angles at a thin prism crosses that prism, suffering or deviating by equal angles. Okay, so remember this point, that's very important for further studies. And also we have a concept of object and image in prism. Suppose we have an object here, and here we have a small prism, a small angled prism. Okay, so thin prism means the angle of prism is a small, A is a small. Let us assume two lights are incident on the prism, also at very small angle of incidence I. The angle would be different, obviously the angle would be different, but both angles I will be very small. Therefore, the both rays will be deviated by equal angles. Remember, both rays will be deviated by equal angles. If this ray is deviated by delta, the second ray also deviates by angle delta. Okay, and these two rays, when extended, do not meet after the prism. If we extend them back, they appear to come from this point. So as this point is intersection point of refracted rays, it becomes image. Suppose this distance is u, the distance of object from prism, and this distance is h. Approximately you can write the angle delta is nearly h divided by u. So h becomes u times delta. And what is delta? You know the deviation by thin prism in case of normal incidence is a times mu minus 1. So it becomes a times mu minus 1. So it is actually the shift of object if we see the object through a prism. It is shifted opposite to the base of prism. See, the base of prism is here, so object is shifted upward, not towards the direction of light or away from it. It remains in its own plane, but is shifted upward, means opposite to the base of the prism. And this is the shift. Always remember, never forget to put the value of A. You have to put the value of A in radians. In radians, remember this. So let us take this question, and here we have a ray incident at an angle of incidence I on one surface of a small angle prism. Let us assume this angle is I only. It is wrong here. And angle of prism is A. They have already said the angle of prism is a small. Okay. And emerges normally from the opposite face. It emerges normally from the opposite face. If refractive index of the material of prism is mu, then angle of incidence is nearly equal to C. Let us take a small angled prism like this. Consider this as very small, and a light is incident on it at an angle I. But as the ray emerges through second face, normally, right, normally this angle must be 90 degree. And if this angle is 90 degree, this is A, this also becomes A. This also becomes A. And refractive index is mu. Now let us apply Snell's law at first phase, and we have sin I equals mu times sin R, which is equal to A. So we have sin A, and as I and A both have very small angles, I and A both have very small angles, we can write sin I as I and sin A as A. So I becomes mu times A. So we have answer D, mu times A. So this is mu actually. So D is mu times A. Okay. Next question. Here we are given that we have a prism of angle 1 degree only, and refractive index 1.5. A good estimate of the minimum angle of deviation in degrees is close to n by 10. Actually, we have to find minimum angle of deviation. But as you remember, for a small angle prism, The deviation is not dependent upon angle of incidence, it is constant. And that value of deviation is equal to delta equals A times mu minus 1. So, if deviation is constant, minimum deviation 2 will have this value. Let us put A as 1 degree and mu as 1.5. So, here we have 1.5 minus 1 as 0.5 and we get deviation as 0.5 degrees. But as they are saying deviation is n by 10, so if we take this deviation as n by 10, the value of n equals 5. So the perfect answer is 5 for this question. Now we will study dispersion. And dispersion in nature is because of a very unique property of transparent medium, and it was discovered by Cauchy. So we say it is a Cauchy's relation, and Cauchy's told us that the refractive index of a transparent medium not only depends upon the properties of medium, it also depends upon the wavelength of light traveling in it. Means, if in a transparent medium, two lights of different color, let's say red and violet, are traveling, the refractive index of medium will be different for red and it will be different for violet because their wavelengths are different. The empirical relation between refractive index and wavelength is something like this, and this says the mu decreases as lambda increases. So as we know, the wavelength of red color is more than wavelength for violet color. That's a very common information. So if wavelength of red color is more, the refractive index of red color would be smaller than refractive index of violet color. As we know, the visible light sequence is V, I, B, G, Y, O, R. It is actually the increasing order of wavelength. So this will be actually the increasing order of mu. The highest refractive index of any material will be for violet color, and the least refractive index for any material will be for red color. So that is an amazing property, and you should keep this in mind that the refractive index is not only the property of the medium itself, it also depends upon the light traveling in it. Okay. As the refractive index for violet color is more, the two lights in any medium will travel at different speed, because the speed of light in medium is given by the c speed of light in vacuum divided by mu. So as mu for violet color is more as compared to mu of red color, right? So obviously if mu for violet is more, the mu will be traveling, the violet color will be traveling, the violet light will be traveling slower than the red light. So we can say the speed of light for violet will be less than speed of light for red. But this is true only if lights are traveling in some medium, because in vacuum all colored light move with same speed, that is 3 times 10 to the power 8 meter per second. Okay. So what is the effect of this property if we consider deviation by a prism? Suppose we have a prism. For convenience of calculations, I am assuming that this prism is a small angled prism, and I hope you all know that deviation produced by prism is A times mu minus 1, right? But as the mu for different colors is different, the deviation too will be different for different colors. As mu is highest for violet, the delta violet means deviation of violet color would be A times mu violet minus 1. So if we send a white light here, suppose we send a white light, as you can see in this diagram also, we have a prism and we are sending white light from one side. Okay. The violet color will be deviated most. The violet color will be deviated most. So when this passes through the prism, the violet is deviated most. And as the deviation for red color would be A times mu red minus 1. As mu red is the least, the deviation for red color would too be least. So we have the least deviation for red color. And all other colors will lie in between these two. So we see that a white light is splits into its constituent colors upon emerging through a prism. And this splitting of light into its constituent colors is called the phenomenon dispersion. Okay, it is called dispersion. We have a very special physical quantity also related to dispersion, and that is called angular dispersion. And what is angular dispersion? Actually, this angle in which light spreads is called angular dispersion, and it is denoted by phi. Right. So the angle in which light spreads is called angular dispersion. Let us see how to calculate it. If we extend the initial direction of light like this, see, this is actually the deviation for red color, and this is actually deviation for violet color. And these are given by these two simple equations. Can you see? So it's very easy to guess that this dispersion or angular dispersion is difference of these two angles or difference of these two deviations for violet and red color. So I can write easily that the phi is given as delta V minus delta R. If you put the values of delta V and delta R here, you will get A times mu violet minus mu R. Okay, and that is the value of dispersion. So if they give you the value of angle of prism, the refractive index for violet and red color, this you can find dispersion from this information. We also say dispersion equals A times d mu. And what is d mu? D mu is actually the difference of refractive index for violet and red color. So this quantity is sometimes also called d mu. Okay. Now we also learn about mean deviation. What is mean deviation? Actually, you have seen delta R is deviation for red color. Delta V is deviation for violet color. And all colors between violet and red lie in between. So actually yellow color is called the mean color. Yellow is called mean color. And if yellow is mean color, the deviation for yellow light will be the mean deviation, and it will be A times mu yellow minus 1. If color is not specified in the question, we would by default assume the color is yellow and deviation is as mean deviation, that A times mu minus 1. Okay. So the next property that is very important in dispersion is dispersive power. It is the ability of a transparent medium to disperse the light into its constituent colors. So let us define what is dispersive power. The definition of dispersive power is actually, it is equal to angular dispersion per unit mean deviation. So you can call dispersive power omega as angular dispersion. What is angular dispersion? Phi divided by mean deviation. This is the definition of dispersive power. And let us write its value. Omega will be equal to, as phi equals A times mu violet minus mu red divided by delta, the mean deviation is A times mu yellow minus 1. So A will get cancelled. And you have dispersive power as mu violet minus mu red divided by mu yellow minus 1. So actually the dispersive power is not dependent upon the shape of the prism, as A got cancelled. It is actually the property of the transparent media. It is not dependent upon the shape or structure of the optical instrument. Okay. If any medium is transparent, it must be having dispersive power and given by this relation. As mu v minus mu r is also written sometimes as d mu, and by default the color we assume is yellow, so mu yellow minus 1 we can write as mu minus 1. So dispersive power is also defined as d mu divided by mu minus 1. And remember the fact that dispersive power depends upon the medium only. It is not dependent upon the shape of that object. Now let us understand what happens if we use 2 or more prism instead of 1. So in first case, suppose we have 2 prisms and the orientation of both prisms is same. Like the vertex of both prisms is on one direction and base is on one direction. Let us say the prism have different angles A1 and A2. The dispersive power may differ, the refractive index may differ. But in this way, as the deviation occurs or light bends towards the base of the prism, if we put a white light here like this, the first prism splits it and also deviates it like this, and the second prism adds the effect, deviates it more and disperses it more. The net deviation here will be given by the deviation by first prism plus deviation by the second prism. When no color is specified, we mean the mean color. So the mean net deviation will be the mean deviation by first prism plus mean deviation by second prism, and the net dispersion will be equal to the net dispersion by first prism plus net deviation by second prism. If we have more prism, the delta and the phi can be added in respective equations. Okay, but what if we have 2 prisms in opposite sense, means their vertex are in opposite direction? What happens here, when we put white light on one, the first prism deviates light towards its base and the second deviates it towards its own base. So the net deviation in fact is delta 1 minus delta 2 at the 2 deviation by 2 are in opposite sense. One deviates clockwise and one deviates anti-clockwise. So net deviation is delta 1 minus delta 2, and also the net dispersion is phi 1 minus phi 2. Sometimes what happens, say the first prism breaks red and violet light like this, and second converges them into one single light, and then we have no dispersion. Then we have no dispersion, and that sort of combination is called the prism combination without dispersion or achromatic combination. So that is a very important point. Achromatic combination. If in a question they ask you how to make an achromatic combination, the meaning of achromatic combination is net dispersion is actually 0. So just find out the net deviation by finding phi 1 minus phi 2, make it equal to 0, and you will get your desired result, or whichever is unknown for you. Okay, let us solve a question on this. The question says variation of refractive index of a crown glass. Crown glass is just a type of material, nothing special. So we have a crown glass thin prism, and the refractive index with wavelength is varying like this. As we also know by Cauchy's relation that the refractive index decreases as wavelength increases. So here we can see the refractive index is decreasing as wavelength is increasing. Now they say which of the following graph is the correct one if dm is the angle of minimum deviation. Dm is the angle of minimum deviation. So if we talk about the deviation, we know that the deviation is equal to a times mu minus 1. The deviation is a times mu minus 1. As wavelength increases, the mu decreases, and as mu decreases, the deviation also decreases. So as in every graph, the wavelength is increasing continuously, the mu will decrease continuously, and if mu decreases continuously, the deviation decreases continuously. So A is your perfect choice already. Next, here we have a thin prism having refractive index, refracting angle 10 degrees. So we have a thin prism of refracting angle, that is angle A as A1 as 10 degree, right? And it is made of glass of refractive index 1.42. So it is refractive index is 1.42. This prism is combined with another prism of glass of refractive index 1.7, and this combination produces dispersion without deviation. So we have net deviation 0. As you know, the net deviation is equal to first deviation plus second deviation, but the net deviation is 0. So it is only possible when the other deviation is in opposite direction. So we must use the second prism in opposite sense. The refractive index of second prism is 1.7, and let's say the angle is A. Okay, and they say we have made a combination without deviation. It is giving dispersion but without deviation. So if we are getting no deviation, then net deviation must be 0. So delta 1 minus delta 2 should be equal to 0. What is delta 1? Delta 1 would be A1, that is 10 degree, times mu minus 1, which is 1.42 minus 1, minus delta 2. Delta 2 would be A times mu minus 1, that is 1.7 minus 1 equals to 0. Okay, you solve this a little. Let us solve it, and we will get 4.2 on the left, 4.2 on the left, and in the right hand we will have A times 0.7, A times 0.7. So A is 6 degrees. So the unknown angle of second prism is simply 6 degrees, and A is your perfect choice. Okay, so let us now study curved surface refraction or spherical surface refraction, I must say. So when light is transmitted from one medium to other and the boundary separating the two medium is curved or spherical, we say it is a spherical surface refraction or curved surface refraction. Suppose we have a boundary here. This separates two medium N1 and N2. The radius of curvature of the boundary is R. We have a real object here. So we have a real object here. And as we have boundary here, the direction of incident light is something this. So this is called pole. And do you remember all distances are measured from pole? So if you measure distance of O from pole, you are actually moving in opposite direction. So here also, if you have a real object, its distance U must be negative. And similarly, you can say if object is virtual, the U will be positive, because in that case light is going this way and object is existing on the right hand side. But with V, the convention is different from that we studied in mirrors. See, if the light after refraction converges at this point, here we get real image. And if we get real image here, this is V. And as you are measuring V in the direction of positive direction from pole, the V is positive here. So if we have real image V will be positive, and if we have virtual image, V will be negative. So this term is different from the mirrors, because in mirror actually the reflected light is reflected back, so direction flips there, and here we see a constant direction of motion of light after refraction. That is why the convention for image is opposite, okay, because there is no change of direction of motion of light. Okay, if we want a relation between object distance and image distance and radius of curvature r, we have n2 by v minus n1 by u equals n2 minus n1 by r, where u, v and r are simply object distances, image distances and radius and center of curvature distances, all from pole. n1 is actually the medium where we have incident light, and n2 we have medium where we have refracted light. Everything is same as we studied in plane surface refraction, but always use this formula with sign convention. And the sign convention is same as we studied in mirrors. The same we have here also. The direction of incident light is considered positive and all distances are measured from pole. Okay, so here we have a question, and in this question they say the eye can be regarded as a single refracting surface. So we have eye as a single refracting surface. The radius of curvature of this surface is equal to the cornea radius, and which is 7.8 mm. So you can imagine the radius as 7.8 mm. Okay. The surface separates two media of refractive index 1 and 1.34. So obviously outside we have air, so we have 1 outside and 1.34 inside eye, and they say that what is the distance from refracting surface where a parallel beam of light will come to focus. So suppose we put a parallel light on the surface and it is focused somewhere here. We have to answer this distance, right? Okay, let this distance is V, and as you can see the incident light is coming from infinity. You can say it is coming from infinity. And now let us use the CSR formula, or curved surface refraction formula. Here we have n2 by v. What is n2? 1.34, because refracted light is in 1.34 divided by v, minus n1. We have incident light in air, so we have n1 as 1 divided by u. But object distance is infinity. And this equals n2 minus n1, that is 1.34 minus 1 divided by r. Can you see? The direction of incident light is this. So this direction is positive, and from pole the center of curvature 2 is in positive direction, so we have r also positive. So let's calculate v from here. V will be equal to 1.34 times r, which is 7.8 mm, and divided by 0.34. If you calculate this, you will get approximately 31 mm as an answer, and the D, which is 3.1 centimeter, is obviously the perfect choice. Next. Okay, this is actually a problem based on mirrors. We have already discussed. Let us solve it again. We have a spherical mirror, and the spherical mirror is obtained by taking a portion of a complete glass sphere, and we have polished the outer surface, so it takes a concave mirror. An object is placed here. See, from here to here the distance is 16, so obviously the center of curvature is at 8. The object is placed at this point, so object is at a distance of 10 centimeter from pole, and they are asking what is the nature of image. So let us apply mirror formula. The mirror formula is 1 by v minus 1 by u. U is 1 by v plus 1 by u, but u is plus minus 10 here, equals 1 by the focal length. And see, as radius of curvature is 8, focal length will be 4, and for concave mirror we have negative focal length, so minus 4. If we solve v from here, we get v equals to minus 1 by 4 plus 1 by 10. Let us solve it a little more. We have 20 LCM, we have minus 5 plus 2. So V comes out to be minus 20 by 3. As V is negative, and for mirror, do you remember, if V is negative, we used to get the real image. So image is definitely real. If real objects, real image is obtained, it will be definitely inverted, right? And the value of V is nearly 6.67. So V is smaller than U. If V is smaller than U, means magnification is less than 1. Magnitude of magnification is less than 1, means the image is smaller also. So we get inverted, real and unmagnified image, that is a smaller image, and D is your perfect choice. Okay. Next question. Yes, here we have a light ray, and the light ray enters a solid glass sphere of refractive index √3. Okay, let's make a solid glass sphere and refractive index is √3. And the angle of incidence is 60. So let us assume this as center of the sphere, this is normal, and light ray enters here with angle of incidence as 60. Obviously it will be refracted inside, and this suppose as angle of refraction. We can calculate this angle of refraction by using Snell's law, and Snell's law gives sine 60 equals √3 sine r. So you get sine r as 1 by 2, because sine 60 is √3 by 2. So r as pi by 6 or 30 degree. So we have r as 30 degree. If I take another normal, if I draw another normal, the light ray is incident again on some other point, and obviously this angle is also 30, because the triangle inside the sphere is isosceles, because these two are equal as they are radii. And this ray separates into two parts according to the question. A part of it is reflected back inside a sphere, and another part is transmitted outside a sphere. If you apply Snell's law for this angle, you will find this angle as 60. The Snell's law will give you this angle of emergence as 60, because again √3 sine 30 will be equal to sine 60, right? So this is 60, and this angle according to law of reflection is 30, because reflection is taking place here. So the angle between refracted ray and reflected ray is this, and this angle is actually 180 minus 30 minus 60, that is 90. So angle between reflected and refracted ray is 90 degrees, right? So this was a little bit about curved surface refraction. We don't get too many questions based on this. The next one is a really very important part. You will find tons of questions in every exam based on thin lenses. Okay, so let us start lenses. Lenses are actually the transparent medium. Lenses too are transparent medium, but that medium should be bounded by two surfaces, and at least one of the two surfaces must be curved. Both may be curved, but at least one of the surfaces must be curved. Then we will have a lens. Like here, in these lenses, we have both surfaces curved. Here we have both surfaces curved. They are also lenses. Here we have one surface curved, one plane surface, one curved, one plane surface. They are also lens. And in the fourth option too, both surfaces are curved. The lenses are categorized according to shapes into many names. They have many names, like we have biconvex, equiconvex. Actually, the two surfaces have two different radii of curvatures like R1 and R2. Then we have biconvex lens. If the two surfaces have same radii R and R, we have equiconvex. If one is plane surface, we call it plano-convex. And if we have both surfaces, convex and concave, in one, we call it concavo-convex. We call it concavo-convex because it behaves like a convex, because it is thick in the middle, right? And similarly, we have few concave lenses. We have concave lenses, biconcave, equiconcave means both radii are same. We have plano-concave, and here we have convex and concave, both surfaces. But as it is thin in the middle, the main nature, the basic nature of this lens is concave. So it is convexo-concave. Okay. So these are the classifications of lenses according to their shapes. But according to optical behavior, what they do in optics, according to optical behavior, they are categorized in two categories. One is called converging and one is called diverging lenses. So converging and diverging is the classification of lenses based on the optical behavior of the lens. Let us first understand what are thin lenses. Can you see here? The lenses have variable thickness. So at some place the lenses have maximum thickness. The convex lenses have maximum thickness in the middle. The concave lenses have maximum thickness at the ends. But if the maximum thickness of the lens is extremely small as compared to the object distance, the image distance, the radii of curvatures, the focal length, etc. If the maximum thickness is very thin, if the maximum thickness is very small, we call the lens as thin lens, right? Remember this point. So let's coming to converging and diverging lenses. What converging lens do? If we put a converging lens, then what they will do? They will converge a parallel beam of light at some point. And the point where they converge a parallel beam of light is called focus point. And its distance from lens is called focal length f. So this is focal length f, right? And can you see the light is traveling towards right? And if light is traveling towards right, this distance is measured from this point. This point is called optical center, not pole here. So distance from optical center of focus point is f, and this is being measured in positive direction. So always remember, converging lenses have positive focus, and diverging lens. What are diverging lens? If we have a diverging lens like this, they will diverge the incoming light, and the refracted light appears to come from this point. So we have focus for diverging lens here, and here you can notice the focal length is negative, because the focal length is measured in opposite direction of positive light. So always remember, converging lenses have positive focus and diverging lenses have negative focus. Students many times think that convex lenses are converging and concave are diverging, but this is a wrong fact. This is a wrong information. Usually it happens, the convex lenses are converging and concave are diverging when the medium of lenses is denser than outside medium. So here obviously the medium of lens, let's say mu lens, is more than mu out. Here also, if mu lens is more than mu out, if it is the case, the convex behaves as converging and concave as diverging. But if you place these lenses in a medium having greater refractive index, means the medium's refractive index is less than the outside refractive index, then the nature will flip. The convex lens will start diverging and the concave lens will start converging the rays. So always remember this, Convex lens is not always converging, concave is not always diverging. They change their nature if they are placed in relatively denser medium. Okay. You can also prove this point after I tell you some mathematics related to the lenses. So, we have lens maker formula here. What is the lens maker formula? If you know the lens material's refractive index, the outside material's refractive index, the two radii of curvatures, then you can know what is the focal length of the lens, and the focal length of the lens is given by 1 by f equals mu lens by mu out. Remember, mu lens by mu out minus 1. If we have air outside lens, mu out is simply 1, and you can write mu minus 1 simply. And then 1 by R1 minus 1 by R2. This formula, remember, it is sign sensitive, so always use proper values of radii of curvatures. And if focal length finally comes positive, the lens is converging. If it finally comes negative, the lens is diverging. This is the only rule here. The thin lens formula. If we have the same medium on both sides of a thin lens, we have the thin lens formula as 1 over V minus 1 over U equals 1 by F. The similar to the mirror formula, but the only difference in mirror formula we had positive sign here, here we have negative sign. Magnification. We call transverse magnification as M, and the definition of transverse magnification is height of image upon height of object. Right. This here is also defined as, also called V by U, that is image distance upon object distance. And in terms of only focal length and U, it becomes F upon F plus U. This is also very useful because if you don't want to calculate V, you have just focal length and U, you can calculate what the magnification is. And if few thin lenses are put in close contact, if few lenses are in close contact, this combined lens behaves as a single lens of equivalent focal length given by 1 upon F equivalent given by 1 upon F1 plus 1 upon F2 plus 1 upon F3, etc. So always remember these formula. All the formula I have written here are sign sensitive, so give a very careful attention to sign of all the terms, including R1, R2, U, V and focal length too, and then only you will get perfect answers. So let us start solving few questions based on this. So suppose we have two identical thin plano convex glass lens. We have two identical thin plano convex glass lenses. Refractive index is 1 point and each having a radius of curvature 20. And they are placed such that their convex surfaces in contact at the center. So we have one plano convex lens like this and one plano convex lens like this, and they are placed such that their convex surfaces are in contact. Okay. This has refractive index 1.5 and yes, and radius of curvature 20. The radius of curvature of the curved face as 20. So let us find focal length f1 of first using the lens maker formula. If we apply lens maker formula for first, we can write 1 upon f1 equals to mu minus 1, because outside we have air, mu minus 1, that is 1.5 minus 1 times 1 by r1. Can you see the first surface is a plane surface, so we have radius of curvature as infinity, and minus 1 by r2. See, this face's radius of curvature is r2, and if you consider the light towards right, its center is going to lie on the left side. So R2 is negative, and we will write R2 as minus 20. So we have F1, solve F1 from here, you will have F1 as 40 centimeter. As this lens also has same configuration, it also has focal length f2 and f2 is equal to f1, right? Flipping the sense or converting lenses like this, it doesn't make any difference on focal length, okay, in case of thin lenses, remember. Now they say the intermediate space between them is filled with an oil of refractive index 1.7. So if we fill the intermediate space with an oil, this liquid oil will make another equiconcave lens, and let us say the focal length of that lens is f3. Now we will think of this lens, the equiconvex concave lens, whose focal length is f3, and let us find f3. Again, by applying lens maker's formula, 1 by f3 equals to 1.7 minus 1 times 1 by r1. And do you know 1 by r1? r1 is this surface whose center is on the left. So we have minus 1 by, actually 1 by r1 equals 1 by minus 20. We have r1 negative. Can you see that? And then we have minus 1 by r2, and see the second surface's radius of curvature is positive, so we have 20. So you get minus 1.4 by 20. Now, as you already know that if you have thin lenses placed in close contact, the equivalent focal length is given by 1 upon f1, f1 is 40, plus 1 upon f2, f2 is also 40, plus 1 upon f3, and 1 upon f3 is minus 1.4 divided by 20. So if you calculate this, you will get 1 by 20 minus 1.4 by 20, that is minus 0.4 by 20. So F equivalent becomes minus 200 divided by 4, which is minus 50 centimeter. So the perfect answer is A, minus 50 centimeter. And as the focal length is negative, the combined lens will behave as a diverging lens because the focal length is negative. Okay. Here we have a convex lens A of focal length 20 centimeter and a concave lens of B of focal length 5 centimeter, and they are placed coaxially. So we have a convex lens and a concave lens. As the distance is not known, let us first draw only convex lens. We have a parallel light falling on convex lens, and as the focal length is 20, the light will be focused at a distance of 20 centimeter from the lens, right? Now we have to place a concave lens at a distance d such that the final ray should be parallel as the initial one. So if we place concave lens somewhere here, the light ray will diverge a little more as the concave lens is diverging here. So we cannot place convex lens, a concave lens there. Let's remove it. And if we place concave lens somewhere here, this may diverge this ray like this if this is the focal length of the concave lens. As focal length of the concave lens is 5, let this is 5 centimeter, and this left us the distance between the lenses as 20 minus 5, which is 15 centimeter. So 15 centimeter is the right choice. Correct answer is B. Next question. Here we have a point object and it is placed at a distance of 60 centimeter from a convex lens. The focal length of the lens is 30 centimeter. And now they say if a plane mirror is placed at 40 centimeter from the lens, then where will be the final image formed and what is the nature of that lens? Okay, let that image. See, actually the focal length is 30 and the object is at 60. Means object is at a distance twice of focal length. So here you know if object is at 2f, the image, the first image by lens forms at 2f. So if we take these two rays after refraction from lens will meet at 60 centimeter from the lens. Somewhere here. Right, at 60 centimeter. This is 40, so this is 20. But as we have a mirror here, the rays at mirror, the rays will incident at mirror and they will be reflected like this. And they will meet here. As this is 20, this must be 20 because plane mirror forms image at equal distance as that of object. So this is 20. And from here, the rays will return back and they again fall on the lens. Can you see the rays falling on lens again are diverging? So this is the real object at a distance of 20 centimeter from the lens. And if we take the lens formula again, we can write 1 over V minus 1 over U. Can you see this time the light is traveling towards left. So left will be your positive direction and right will be your negative direction. As the object is at a distance 20 centimeter from the lens towards right, we have U as minus 20 equals to 1 by 30. So we will get V as 1 over V as 1 over 30 minus 1 over 20. So from here you can solve V as 60 centimeter, right? 60 centimeter. Oh, sorry, minus 60 centimeter. And if V is minus 60 centimeter, it means the image is definitely virtual, right? And if image is virtual, it is formed in negative direction at a distance of 60 from lens. So final image is formed at a distance 60 from lens somewhere here and it is virtual, right? So if it is 60 centimeter from lens, we have 40 this, we have 20 this. So let us read the options. It is, yes, it is, as it is 60 centimeter from the lens, it is only 20 centimeters from the plane mirror and it would be a virtual image as V is negative. Okay, so D is your perfect choice. Let's move to the next question. Here again we have a convex lens and it is put 10 centimeter from a light source and it makes a sharp image on the screen. Okay, so we have a convex lens and it is at a distance of 10 centimeter from an object and it forms a sharp image on a screen placed at 10 centimeter from the lens. So this is a screen and as both distances are 10 centimeter, you know that the U and V are equal when they both are 2f. So this must be twice of focal length, this must be twice of focal length. So the focal length of lens is 5 centimeter. Then they say that if a glass slab of thickness 1.5, refractive 1.5 is placed in contact with a light source, means here we place a light source. Obviously the slab shifts, the light source in the direction of incident light. So effectively for lens, the object will be closer than 10 centimeter because of the shift, right? So if u changes, for lens u changes, the image distance v also changes. And to get the sharp image again, you will have to shift the screen for the new image position. So let us calculate how much shift is caused by this slab. I think you remember the shift caused by slab is equal to the thickness 1.5 times 1 minus 1 upon 1.5, and you will notice this will be 3 by 2 times 1 by 3, that is 1 by 2. So we have shift as 0.5. If shift is 0.5, the object distance from lens would be now 10 minus 0.5, that is 9.5. So we have u as 9.5, obviously negative if you take sign convention into account. So now we have 1 over v minus 1 over u, which is minus 9.5, equals to 1 over 5, because 5 is the focal length of the lens, right? And now let us solve this. 1 upon v equals 1 over 5 minus 1 over 9.5. If you take as this, okay. Let us take 95 as LCM. We have 19 minus 10 as 9 by 95. So we have v nearly equal to 10.55 centimeter. 10.55 centimeter. Okay. So initially the screen was at 10 centimeter. And the now screen should be at 10.55 centimeter, means screen should be shifted 0.55 centimeter away from the lens. So the perfect choice is 0.55 centimeter away from the lens, and D is your correct answer. Okay, over to next question. Here again we have a plano convex lens of refractive index mu1 and focal length f1. Okay, so we have a plano convex lens, mu1 and f1 as refractive index and focal length of the lens, right? And we have another plano concave lens of refractive index mu2 and focal length f2. So we have a plano concave lens mu2 and f2. If the radius of curvature of the two spherical faces is r, then and f1 equals to twice f2, then we have to figure out a relation between mu1 and mu2. So let us say the radius of curvature is r for both. Since all these things are related by lens maker formula, let us apply lens maker formula for the two. I'll write 1 upon f1 as mu1 minus 1, and as the first surface is plane, we have 1 upon r1 as 1 upon infinity minus 1 upon, see r2 is negative because we are considering the light going in right direction. So r2, so which is r, is negative, so we have minus r. So we have f1 as r upon mu1 minus 1. Similarly, if you solve f2, you will get f2 as r upon mu2 minus 1 with a negative sign, because there the r will be negative. Okay, now we have f1 equals to 2f2. Okay, so let us write f1 as 2f2. Okay, in magnitude, obviously in magnitude. So I'll write r divided by, let me write f1 equals to f2, and obviously this relation is in magnitude, so I can write the magnitude f1 as r upon mu1 minus 1 equals to twice of r upon mu2 minus 1. So r got cancelled, we have mu2 minus 1 as 2 mu1 minus 2. So let's bring it here, we have 2 mu1 minus mu2 equals 2 minus 1, that is 1. So we have 2 mu1 minus mu 2 equals 1, right? And obviously 2 mu 1 minus mu 2 equals to 1, so D is your perfect choice. Next question. Here we have an object and it is at a distance of 20 meters from a convex lens of focal length 0.3 meters. And if object is moving away from the lens at a speed of 5 meter per second, the speed and direction of the image would be as according to 1 over v minus 1 upon u equals to 1 by f. If you differentiate this formula with respect to time, we have done it many times. The dv by dt, that is velocity of image, is actually equal to v square by u square times du by dt, that is velocity of object. The v by u is actually magnification. So we can also write it as magnification square times du by dt as velocity of object. Let us calculate magnification separately. As we know, magnification in lenses equals f upon f plus u. But for convex lenses, we have positive focus. So we have focus as 0.3 divided by 0.3 plus, and u for real object is always negative. So we have minus 20 here. So magnification becomes 0.3 divided by minus 19.7. And if you place the magnification's value here, square it, so minus term won't affect a thing, right? So you will have dv by dt as m square. What is m square? M square is 0.3 divided by 19.7 square and times object velocity, and object velocity is 5 meter per second. 5 meter per second. As we have magnifications square here and a square of any negative quantity is also positive, we have the image velocity in same direction as object velocity. And as in case of lenses, if object is here and image is here, as they both are real, object is moving away from the lens, so object is moving towards left. As image is also moving in object's motion direction, image is moving towards left, so obviously image is moving towards the lens. And if you solve this calculation, you will get nearly this as the perfect result. So we will have image velocity as this, and image would be moving towards the lens. Okay. Now let us see what we have next. Here we have what is the position and nature of image formed by lens combinations shown in figure. F1 and F2 are focal lengths. So we have two lenses, both have equal magnitude of focal length, 5 centimeter each. One is positive, one is negative. Object is placed at a distance of 20 centimeter from this lens, and the gap between the two is 2 centimeter. And we have to know what is the position and nature of image formed by this combination. So first we will consider refraction by first lens. First lens. Okay, let us apply 1 over v minus 1 over u, which is minus 20 obviously, equals to 1 upon f, which is 5. And from here you will see 1 over v equals 1 over 5 minus 1 over 20. Multiplied by 4, you will have 4 by 20. 4 by 20. And as a v, you will have 20 by 3. Which is almost 6.67 centimeters. So the first image forms somewhere here. This is the first image I1 made by first lens. okay, and it is formed here. But this image will make an object for the second lens. And as this distance is 20 by 3, this distance from second lens would be only 20 by 3 minus 2. So when we consider the second lens, yes, can you see on second lens the incident rays are actually converging. So we have a virtual object with a positive U, and the U would be 20 by 3 minus 2. So obviously it becomes, yes, 14 by 3. Okay, 14 by 3, 20 minus 6 by 3. Okay, yes. So for second lens we have 1 over V minus 1 over U. U is 14 by 3 equals 1 upon minus 5. Now let us calculate this. So 1 over V equals 3 by 14 minus 1 by 5. Okay, if we take 70 as LCM, we have 15 minus 14 here. So we have V as 70 centimeter. And also we are getting positive sign. It means as we are getting light in moving in right direction, and finally V is positive. If V is positive in lenses, it means real image, and the real image is formed at a distance of 70 centimeter from concave lens. So let us see. Yes, it is 70 centimeter from point B, which is the place of concave lens, and the image will be real as we are getting positive. So always remember the fact, in case of refraction or in lenses, the U is negative for real object, positive for virtual object, but V is positive for real image and negative for virtual image. So whenever you see V positive, it means real image in lenses or in refraction, and V positive in mirrors means virtual image. Let's see what we have next. Yes, here we have a Plano convex lens again of focal length f2 and refractive index mu2. So we have a Plano convex lens of focal length f2 and refractive index mu2. And we also have a Plano concave lens, and both fit exactly into each other. Means we have a Plano concave lens like this, and both fit means they have common radius of curvature. They have same radius of curvature, common radius of curvature R. And the other's focal length is f1 and refractive index mu1, right? Their plane surfaces are parallel to each other, as we can see in the diagram. Then we have to answer what is the focal length of this combination. So let us see what is the focal length of this combination. Obviously we have focal length as f1 and f2. One is positive, one is negative. So if you try 1 upon f equivalent as 1 upon f1 plus 1 upon f2, that would be right. But there is no option according to that result. So we will have to try something else. Okay. If we combine them according to lens combination, we will have to write 1 upon f equivalent equals to 1 upon f1 minus 1 upon f2, as the second lens is concave, and the f equivalent would be f1 f2 upon f2 minus f1, but with this no option matches. So in terms of f1 and f2, the right answer is this, and nothing matches, and these three options are in terms of f1 and f2. So obviously A is wrong, B is wrong, and D is wrong. So automatically C becomes the right one. But if you want to try it yourself, let us find f1 and f2 in terms of radius r. So we apply lens maker formula for 1, and for 1, if you apply lens maker formula, you will see the F2 as R upon mu 2 minus 1. This is the result of lens maker formula, don't forget. If you apply lens maker formula for lens 2, you will have F1 as minus R upon mu 1 minus 1, right? And as the net focal length is 1 over F equivalent as 1 by F1 plus 1 by F2, we can write F2 is actually positive, so we can write F1 as mu 1 minus 1 by minus R, or let us say minus R, and plus mu 2 minus 1 by R. If you combine the result, you will have mu 2 minus mu 1 by R. So F equivalent becomes R upon mu 2 minus mu 1. So in terms of R, mu 1 and mu 2, the result is simply C. Can you see that? Okay. Let us see what we have next. Here we have a point-like object placed at a distance of 1 meter in front of a convex lens of focal length 0.5 meter. So if object is placed at a distance of 1 meter and focal length is 0.5 meter, obviously object distance is twice of focal length. And if object distance is twice of focal length, the image distance too will be twice of focal length. So we have object's image somewhere here at a distance of 1 meter. A plane mirror is placed at a distance of 2 meter behind the lens. The position and nature of final image formed by this system will be. Okay, let us see. Let us shrink this diagram a little. We have a convex lens. We have some object here at 1 meter. As focal length is 0.5. So object distance is twice of f. So image distance is also twice of f. So we have image here at 1 meter. Now we have a mirror 2 meter from lens, that is 1 meter from the image. Let us see how the light propagates. If you take two light rays from object, they are definitely going to meet at I, and they proceed further, and they are incident on the mirror. The mirror forms virtual image I2 here, and then again the light reflected by plane mirror is incident back on the lens, and as this is 1 meter, this is also 1 meter. So this I2 works as the object for the lens again, and light is traveling in this direction now. So this is positive direction. So can you see the object is at 3 meter from the lens, right? It is 3 meter from the lens, and u is negative 3 meter because this is now negative direction as light is traveling left after reflection. So if we consider the third event, the first event being the refraction from lens, the second being reflection from mirror, and third being again refraction from lens. In the third event we have 1 upon v minus 1 upon u as minus 3 and equals to 1 upon 0.5 because the lens is converging. So we have 1 over v as 1 upon 0.5 minus 1 by 3. If you multiply 6 on numerator and denominator, you will have 6 by 3 here, and it will become 6 by 3 minus 1 by 3, that is 5 by 3. Okay, so V is 5 by 3. And if V is 5 by 3, V is positive. 5 by 3, you can write 5 by 3 as 0.6 meters. So positive means, finally, if you just extend the lens a little more, these light rays converge at some point here and the V is 0.6 now. As V is positive, we have the real image, the final real image. Okay, and from lens, the distance of image is 0.6. But from mirror, the distance is 2.6. So obviously, the D is your correct choice. 2.6 meters from the mirror and the image is real. Here, they say a double convex lens has power P and same radii of curvature on both sides. Then what will be the radius of curvature of one side of a plano convex lens made of same material and with power 1.5 P? So let me first define what is power actually. So the power is actually the converging ability of any mirror or lens, and mathematically power of mirror is defined as minus 1 upon f, where f is the focal length of the mirror. In SI units, the unit of power is diopter or D, and you will get the correct value if you put the value of focal length in meters. Remember that, okay? But if you want to calculate the power of a lens, the power of lens is defined as simply 1 by f, and again the unit is diopter if you put the value of focal length in meters. Remember that, okay? So as the radius of curvature of both the surfaces is r and we have power P, and let us say the refractive index is mu. According to lens maker formula, we know 1 upon f, which we now know is power. So power equals mu minus 1, and 1 upon r1 minus 1 upon r2 for a convex lens will give you 2 by r. So we have a relation relating P, mu and r. Let's write it as this. And in second case, we have a plano convex lens of some other radius and power 1.5. So if we have a plano convex lens of power 1.5 P, this can be written as, according to lens maker formula, the mu minus 1, and since we have only one surface, here we will get 1 by r. Equation number 2. Now let us replace mu minus 1 from both the sides, or let us just divide these two equations. On the left we will get 1 upon 1.5, that is 2 by 3, and on the right we will get, actually the radius is different here, and that is asked. Let us suppose the radius of plano convex lens is r dash, okay? So it is not the same as before. So here we get 2 r dash by r, and if you calculate the right value, you have r dash as r by 3. So the perfect choice is A, r by 3. Over to next question. Here we have a point object in air and in front of the curved surface of a plano convex lens. So we have a plano convex lens and before it we have a point object in air. The radius of curvature of curved surface is 30 centimeter, refractive index is 1.55, and they are asking us what is the focal length of the lens. Okay, so the focal length of the lens, this is 30 centimeter and the refractive index is 1.5. So we do not need the object because focal length is independent of the position of object. We have to simply apply lens maker's formula once, and according to that 1 upon focal length equals mu minus 1, which is 1.5 minus 1, which is 0.5 times 1 by r1. So 1 by r1 is 1 by 30 and minus the second surface is the radius is infinity. So we have focal length as 60 centimeter. So correct answer is 60 centimeter. Okay, let's move to next question. Now we have a case where the same size images are formed by convex lens. When object is placed at two positions, one at 20 centimeter and one at 10 centimeter from the lens, what is the focal length of that convex lens? Okay. So let us make a convex lens. Okay. As the two same size images are being formed for two different positions of the object, the magnitude of magnification is same in the two cases. And as you know, the magnification is given by f upon f plus u. So for two different positions of u as 20 centimeter and 10 centimeter, we must get different magnitudes or different values of magnification. But as magnitudes are same, the only possibility is that one magnification is positive and other magnification is negative. Means one image is virtual and other image is real. One image is erect and other image is inverted. So that is possible if we place object in between pole and optical center and focus point, and for this case we have a bigger sized virtual image, right? And if we have your object away from focal length, we have a big sized real image, right? As you can see, this distance is smaller and this is bigger. So a smaller distance must be 10 centimeter and the bigger distance must be 20 centimeter. Let us now assume the magnitude of magnification. Let magnitude of magnification is m. And if magnitude of magnification is m, this distance, as m is v by u, v is m times u, this distance must be m times 10 and this must be m times 20, because at both cases we get same sized image, so we get equal ratio between v and u. Okay. So if we apply lens formula for the two cases, for first case we have u as 10 centimeter, v as 10 centimeter and v as 20 m centimeter, sorry 10 m centimeter, both negative. So according to lens formula we have 1 upon minus m10 minus 1 upon minus 10 and it is equal to f. And for second case, the same 1 upon f, because we have same lens, the same 1 upon f equals 1 by v, which is 1 by 20 m and minus 1 upon minus 20. Let us solve this. Okay. So here we have minus 1 by 10. Let's cancel 0 from every term, and here we have minus 1 by m. Let's also multiply the whole equation with the minus sign, then we have 1 by m minus 1, and here we have minus 1 by 2, and here we have minus 1 by 2. Here we have minus 1 by 2m. Okay. Let's bring this here and 1 there. So we have 1 by 2m equals 3 by 2. 2 got cancelled. So we have magnitude of magnification as 3. Means for real image we have magnification as minus 3, and for virtual image we have magnification as plus 3. And now we understand, in first case we have object distance as 10 and image distance as 30. So now we can calculate the focal length also by applying the length formula for any of the case. So let us take the first case. We have V as minus 30 minus 1 upon minus 10 equals to 1 by F, right? And here we have 1 by F equals, we can make it positive, and let's say 3 by 30. So we have 3 by 30 minus 1 by 30, that is 2 by 30. So focal length comes out to be 15 centimeter. 15 centimeter. That is your right answer. Let us move to the next question. Okay. Sorry, we now have a new concept in thin lenses, and that is displacement method. And with displacement method, we are able to find the focal length of a converging lens. So let us study what is displacement method. There is one thing you all should always remember, which is important here, is that the minimum distance between a real object and its real image by a converging lens is 4f. Means if you take a lens and put your real object at 2f, its real image is formed at 2f. So the distance between object and image is 4f. And if you move this object a little, image moves in same direction, and such that the gap between object and image always increases. Like if you move this object towards lens, the image moves away from the lens, but by a bigger distance. If you move object towards left, the image also moves towards left, but by a smaller distance. So that is why the distance between object and image always increases, and the minimum distance between real object and real image is always 4f. Okay. So what is the principle of displacement method? Let us study. Here we have fixed object and fixed screen. What is a screen? You can say screen is the position at which we get image. So basically positions of image and object are fixed. And now we take a lens. This distance is called capital D, and as we get image on a screen, the image should be real and object is also real, so this D should be more than 4f. So D should be well more than 4f. Okay. Suppose now we have a lens whose focal length is to be found. If you place that lens in between the space, you will notice that at two positions of lens, these are not two different lenses, but actually the same lens at two different positions in two different cases. So at two positions of lens, you will get the same object's image on the same screen twice. So if this is the first position of lens and you get a sharp image on the screen, just notice, let's say this is x and this automatically becomes D minus x. Okay. And next time when lens is placed somewhere here and again the sharp image is obtained, just measure this and you will find that this distance as D minus x and this as x, because obviously the u and v are interchangeable. If you place object at the place of image, definitely the image will be at the place of initial object. So you can remember this fact that the two positions of lens are actually symmetrical with respect to object and screen or image, you must say. So if we just look at the diagram and just try to summarize the results, in first case you can write M1. M1 is the magnification in first case, that is height of image 1 divided by height of object. Obviously, object is 1 but images are 2. So, height of image 1 divided by height of object, and that is actually d minus x divided by x, and obviously negative. Because we have real image, we have inverted image. Similarly, I can write m2 as hi2 by ho, and this equals minus x divided by d minus x. And if you multiply these two, you have m1, m2 as 1. Obviously, the multiplication of these two would 2 be 1, and that gives you hi1 times hi2 equals to ho square. Means the object height is actually geometric mean of the two image heights obtained. Second result. As we now know by measurement, the 2u and v, the value of x is known, and b, the already known quantity, d is an already known quantity. So, if x is known and d is known, you can place u as minus x and v as d minus x in where? In length formula. And as you have noticed, you have measured x, you can now calculate the focal length of the lens. So, it will be given by 1 over v, which is d minus x, minus 1 over u, which is minus x, equals to 1 over f. So, from here you can calculate the value, the focal length of the lens. Let us now solve a question based on this. So, it says, the question says the distance between object and screen is 100 centimeter. So, we have object and screen, and the distance between the two is 100 centimeter. Right? A lens can produce real image of the object on a screen for two different positions between the screen and the object. So, now you remember, we have two positions of lens, and the two positions are actually perfectly symmetrical with respect to object and the screen. The distance between these two positions is 40 centimeter. So, this distance is, the gap between the two positions is 40 centimeter. So, because of symmetry, you can say this must be 30 and this too must be 30, because 30 plus 30 plus 40 is 100. So, let us take the first position of lens, and for first position of lens, the u becomes minus 30 and the v becomes 70. And let us use the lens formula. We have 1 divided by v, which is 70, minus 1 divided by u, which is minus 30, and here we have 1 upon f. Okay, so let us calculate. So, 1 by f becomes, let us take 21 0 LCM, and we have 3 minus 3 plus 7. So, the focal length becomes 21 centimeter. So, as focal length is 21 centimeter, we can now calculate power, and power is 1 divided by focal length in meters, which is 0.21. But as power is n by 100, you can now calculate n, and n would be very close to 476. So, perfect answer for n is 476. Now, let us move to the next concept of optical instrument. The instruments which help us to see the objects which are either very small to see or which are very far from us to see, those instruments are called optical instrument. Our spectacles are actually an optical instrument. The lenses, the magnifying glasses, the microscope, the telescope, they are actually optical instruments. Even our human eye is also a very complicated and very intelligent optical instrument. Okay, so let us learn two important facts about human eye. The first is the eye can observe only angular size. The eye can observe, eye has no idea of linear size. Means suppose we think of an eye, and in front of this eye we have two objects, one this of length L1, one this of length L2. Both are different, but the eye will observe them as equally big because they make equal angle on eye. So eye has no clue of linear size. As you must have seen that when we see an aeroplane flying in the sky, it looks very small because it makes very small angle on our eye, and when you look at the airplane in front of you at airport, it looks very big because it makes very big angle on eye. Okay. The second point is, if you place some object very close to your eye, means if you place a object very close to your eye, like less than 25 centimeter, that like 10 centimeter or 5 centimeter, the object looks blurry to you. You cannot see its sharp image. So actually the eye too has some limitations, and you can see, or our human eye can see objects clearly if the object distance from eye is more than 25 centimeter. This 25 centimeter is for actually a healthy human eye. So if object distance is more than 25 centimeter or up to infinity. So if object distance is between 25 centimeter and infinity, then we can see the object clearly or sharply. Okay. This point, the 25 centimeter, is called near point, and this infinity is called far point. So object should be between near point and far point, anywhere in between, so that we will look at it very sharply. So let us learn few important terms in optical instrument. So the first is angular magnification. As angular magnification becomes very important here, the reason being eye can see only angular size. Okay. So angular magnification is defined as M angular. It is defined as beta by alpha. Beta by alpha. Beta and alpha, what are beta and alpha? They are basically the angles subtended by image and object on eye. So beta is angle subtended by final image on eye, and alpha is actually angle subtended by object on eye. So this is actually the angular magnification. But there exists one more very important physical quantity here, and which is magnifying power. What is magnifying power? Magnifying power sometimes confuses us with angular magnification, but it is different from angular magnification. And the magnifying power's definition is actually again beta by alpha. But what is beta? Beta is actually same, the angle by final image on eye. It is same as above. Same as above. But what is alpha? Alpha is actually the angle by object on eye when object is placed at a certain location or when object is placed at near point. So in magnifying power we have a condition. So if we want to calculate alpha for finding magnifying power, we will have to place our object at a distance of d, where d is nearly 25 centimeter. So we place object at a fixed position, means at near point of eye, and then the angle it makes on eye is called alpha. Remember this? So as objects that we see from microscope are very small, and when we place them at a 25 centimeter distance from eye, they make very small angles on eye. Looking at tables and chairs, objects like umbrella and TV, it doesn't make any sense to see them through microscope. Through microscope, we see only tiny objects, which are very tiny, and obviously they will make very small angle when placed at a distance 25 centimeter. So usually this alpha is very small, and if alpha is very small, alpha can be written as tan alpha. Approximately you can write alpha as tan alpha, and tan alpha would be height of object divided by d. So the definition for alpha is h divided by d, and it is a common definition for alpha in microscopes. Okay, so let us first understand the simplest kind of microscope means a magnifying lens. A simple magnifying lens is called simple microscope. So this is a simple microscope. Here we have a convergent lens, that's it. And when an object is placed somewhere between optical center and focus, a virtual image is formed. A virtual image is formed, and can you see this virtual image forms an angle beta on the lens, and behind the lens we have eye, so we can say the image forms an angle beta on eye. Right. So if we want to calculate its magnifying power, I can write the beta as this height divided by this height. But by similar triangles, you can also write beta as this height divided by this distance. And as this height is h, the object height, divided by u, you can write beta as h by u. And alpha has a fixed definition that h by d, cancel this h and you get m equals d by u for simple microscope, right? But as the eye, the observer, looks at this image through this lens, this image must be, let's say this is V. Let's say this is V. So this image must be between near point and far point of the man, right? So this V should be less than infinity and should be more than or equal to 25 centimeter, which is also called D. So if we wish to see the image at infinity, this case is called looking at the image with relaxed eye, or it is also called normal adjustment. Remember this point? If image at infinity, if we see image at infinity, this is called looking with relaxed eye or normal adjustment or normal adjustment. Okay, so if image is at infinity, if you want your image to be at infinity, you should place your object at focus, and the object distance becomes the focal length. And if object distance becomes focal length, u becomes focal length, the m becomes d by u. So in this case we have m, which is d by u, and u becomes focal length. So this is the magnifying power in case you look at the final image at infinity. Okay, but if you see image at minimum distance of clear vision, means at near point, if image at D, you can again find the magnifying power. If image is at D, you know the value of V as D. Now you can calculate the value of U by using lens formula. So let's skip that calculation. I'm just writing the magnifying power, and here you get magnifying power as d by f plus 1. So we get bigger magnifying power. Remember, we get bigger magnifying power in case the image is seen at day. So actually this time your eyes are a little strained, but you get an advantage of bigger magnifying power. Means object looks even more bigger, even more nearer to you, right? So let's move. Then we have compound microscope. And what is a compound microscope? In compound microscope, we have two convergent lenses, remember. Two convergent lenses, right? The first lens forms real image of the object, and the second lens forms the virtual image of the real image formed by the first lens. Okay, the first point. The second point, the lens which faces object is called objective, and the lens which faces eye is called eyepiece. Actually, if you look at this diagram, you will see that it is exactly similar to the simple microscope. So eyepiece here also serves as a simple microscope, and it has the same magnifying power as we discussed earlier. But because of this lens, because of the presence of this lens, we get better magnifying power because its magnification also gets multiplied with magnifying power. So actually the formula for magnifying power here in compound microscope is magnification produced by objective lens multiplied by magnifying power of the eyepiece. And the magnifying power of eyepiece is same as magnifying power of the simple microscope, that is m by u. There are a few more things. Actually this MO is actually image distance for objective lens and object distance for objective lens. But here in this case, actually this is image distance for objective lens, but here this distance is very small as compared to the whole distance. So you can say this distance is actually very close to the distance between lenses, and the object is placed very close to the focus of the objective. So you can write VO as the length of tube and UO as FO. So it is an approximate result and it works well in every situation. So always remember magnifying power is L by FO. If you see the object and image positions are not known to you properly in case of objective, and if they give you the tube length and objective focal length, always remember MO can be approximately written as L by FO. And then we have it is not M actually, it is D by U and D by U. Here also we have two extreme cases, as if you see image at infinity, that is a normal adjustment. In normal adjustment, we have magnifying power as L by FO and D by FE. What is FE? FE is the focal length of eyepiece. And when image at near point, which is D, we get an advantage of 1 in simple microscope. So we get that advantage again, and we have MO, which is L by FO times D by FE plus 1. So it is easy to remember. Just the formula for simple microscope is actually modified by magnification of objective everywhere. And magnification of objective is either VO by UO. If you are given focal length and UO, you can easily find VO, then always use MO as VO by UO. But if tube length and FO are only given quantities, approximate MO by L by FO. Okay, so this was all for compound microscope. Let us see what we have next. So here we have a compound microscope, and the magnified virtual image is formed at a distance of 25 centimeter from the eyepiece, means at near point. The focal length of objective lens is 1, the magnification is 100, and the tube length of the microscope is 20. Then the focal length of eyepieces. Everything suggests this formula. As we have the image at 25 centimeter, right? We can write the net magnification as tube length by FO as magnification of objective and multiplied by D by FE plus 1. Let's put the values. At the net magnification is we have 100 here. Yes, net magnification is 100, so let's write 100. The L is 20 centimeter and FO is 1 centimeter, so we have 20 divided by 1, and here we have D as 25 divided by FE. FE is to be known plus 1. So can you see from here your FE will be equal to, we have 5 here, 5 minus 1 is 4, so the FE has 25 by 4, so we have FE as nearly 6.25 centimeter. So we have FE as 6.25 centimeter. Simple. Next question. Here we have a compound microscope consisting of an objective lens of focal length 1 centimeter, eyepiece of focal length 5 centimeter with a separation of 10 centimeter. So we have an objective of focal length 1 centimeter, eyepiece of focal length 5 centimeter, and gap between them is 10 centimeter. The distance between object and objective lens at which the strain on the eye is minimum is, see, strain on the eye will be minimum when the eyepiece has its object at focus. So the image formed by first lens should be formed at the focus of eyepiece, means this must be 5, and if this is 5, as this is 10, this is also 5. So object in front of objective should be placed at such a distance UO that this objective of focal length 1 centimeter forms image at 5 centimeter. Let us apply lens formula. We have 1 by 5 minus 1 by UO equals 1. So we have 1 by UO as 1 minus 1 by 5. You calculate it, you will get 1 minus 1 by 5 as 4 by 5, right? So your UO is equal to actually minus 5 by 4. Okay. Now they say the value is n by 40. So as value is n by 40, you can make it equal to n by 40. Ignore the negative sign and you will get n as 50. So the perfect answer is 50 for n. Okay. In this question, we need a magnification of 375 from a compound microscope of tube length 150 and objective of focal length 5 mm. What is the focal length of eyepiece? So let's solve it. As we know, the magnification m is equal to the tube length divided by FO times D by FE plus 1 when object or the final image is at near point. We do not have here this one if image is at infinity. So actually, as this is not clear in the question whether the final image is at infinity or at near point or anywhere in between, we are at this position cannot decide whether we should use this one or not. So let us continue with this. As magnification is 375, length we have as 150 mm, so 150 divided by 5 mm, and we have D by FE plus 1. So let's cancel this, and I think you have D by FE plus 1 equals 12.5. So if we do not have this one, we have Fe as simply d by 12.5, as d is 25 centimeter, will be having 2 centimeter. But that is not an option. 2 centimeter is not an option. So let us take this one, and if take this one, your Fe will come out to be 25 centimeter divided by 11.5, and this gives us a little bigger value than 2, that is 2.2 something. So we have 22 mm as perfect choice. Okay, let's move for the next concept, that is astronomical telescope. With microscopes, we see tiny objects but which are very close to us, we can touch them. But with telescopes, we see objects which are very far from Earth, sometimes very far from the even our galaxy. Okay, so we cannot take them and put those objects at near point. So here the magnifying power is not applicable. Here the magnifying power is not applicable. Here the applicability is of angular magnification, and the angular magnification here is equal to beta by alpha. The beta is angle by final image on eye, the alpha is angle by initial object on eye, and there is no condition of putting object at near point because we cannot do that. Okay, here again we have two lenses, two convergent lenses. One is called objective and another is called eyepiece. As object is at infinity, all the rays come from infinity and they focus at focal plane of objective. So this length is always the focal length of objective, and this is called UE because the first image by objective lens becomes object for the second lens, and the second lens again works as a simple microscope here. Okay, if we want magnifying power, the formula for magnifying power here is actually FO divided by UE. What is UE? The object distance. Okay, but for normal adjustment, we have UE equal to Fe because image is at infinity. So we have magnifying power as FO upon Fe, and as the gap between the two lenses, is FO plus UE. Remember, the gap between two lenses or tube length is basically the distance from here to here, which is equal to FO, and from here to here, which is equal to UE. So L is FO plus UE, right? So as in this case we have UE as Fe, the length becomes simply FO plus Fe. Remember, this is a very important point. And if we see final image at D, now you can calculate UE from lens formula, and here you will find UE as dFe upon D plus Fe in magnitude, right? And then your magnification, angular magnification becomes FO upon UE, and the length becomes FO plus UE, where UE is this value. So again, it's all very simple, and let us solve few problems based on telescope, and which are very important problem obviously. So here we have an observer looks at a distant tree of height 10 meter with a telescope of magnifying power 20. So we have a telescope of magnifying power 20. To the observer, the tree appears. As the magnifying power is 20, these two options can easily be removed. But there is always a doubt whether it will look 20 times taller or 20 times nearer. But actually the eye perceives only angular size, as I told you earlier. Eye perceives only angular size, and when you see the aeroplane at a very far distance, it looks small, and when you see it at a nearer distance, it looks bigger. So if something looks bigger, the eye perceives as it is very close to you. So actually the telescope magnifies something by bringing it not in real sense, but it appears that it has brought that thing very close to you. So 20 times near is the perfect choice actually. Next we have an astronomical telescope, and it is a normal adjustment. Remember, in normal adjustment, the magnification is actually FO upon FE, remember. Now they say a black line of length capital L is drawn on inside part of objective lens. So we have an objective lens, and on this lens we have drawn a line of length L. And here we have eyepiece of focal length FE, FO. As it is a normal adjustment, the tube length is actually FO plus FE. And they say the image is formed has length small l. So if image is of small l, we have linear magnification M as small l by capital L. And as we remember, the M is equal to F divided by F plus U. Let's put all the values. As we are considering image by eyepiece, the focal length is FE divided by FE. But as the object of eyepiece is at here, it is drawn here. So the distance U is FO plus FE. So I should write minus FO plus FE. And the L by L term is equal to negative of FE divided by FO. So as FE by FO is small l by capital L, FO by FE in magnitude is equal to capital L by small l. So this is your angular magnification for telescope, right? Let's move to next question. So in next question we have, and again an astronomical telescope has objective and eyepiece of focal length 40 centimeter and 4 centimeter. So we have 40 centimeter and 4 centimeter. An object is at 20 centimeter away from objective. Sorry, 200 centimeter away from objective. So if object distance is given, we can apply the lens formula for objective to find where image forms. So let us say image forms at V0, right? 1 by V0 minus 1 by minus 200, as it is negative, equals 1 by 40. And let us solve this. We have 1 by V0 equals 1 by 40 minus 1 by 200. And from here you get V0 equals to 50. So this much is 50. And if this much is 50, obviously the tube length must be bigger than 50, and the only option with bigger than 50 is D. So D is your perfect choice. Also, you know that this image forms very close to the focal length of the eyepiece, and the focal length of the eyepiece is 4, so it is nearly 50 plus 4, that is 54. So that is answer for this question. Next, here we have a telescope of focal length of objective as 15 centimeter, focal length of eye is 1 centimeter, right? See, if the tube length is 16, I think you know that tube length equals to FO plus UE, and as tube length is 16, FO is 15, you get UE as 1 centimeter and FE is also 1 centimeter. So we see the first image is at focus of the eyepiece, and if first image is at focus of eyepiece, we get final image at infinity, and if final image is at infinity, it means this telescope is a normal adjustment, and in normal adjustment the magnification is given by FO by FE. So we have 15 divided by 1 as 15, the magnifying power or magnification of telescope. So here we have our answer. Next, Let's see what's next. The magnifying power of a telescope with tube length 60 centimeter is 5. So we have tube length as 60 centimeter and magnifying power is 5. M equals 5. 5. What is the focal length of its eyepiece? Okay, if magnifying power is 5, I think you remember magnifying power equals to FO divided by FE. So FO is 5 times FE, right? And the tube length is actually FO plus FE, which is 60 equals to. So if we put, as we have to know the focal length of eyepiece, in place of FO we can write 5 FE. So 5 FE plus FE equals 60. So FE becomes 60 by 5, which is equals to 10 centimeter. So the focal length of the eyepiece is simply 10 centimeter, and that is the perfect choice. So dear students, that's all for today. I hope you have learned a lot in this session, and I've tried to cover every basic concept that is required for NEET and JEE mains. Not even a single stone is unturned. So I hope you have enjoyed it. You have learned a lot. See this session in parts of 1 hour, not more than 1 hour, and try to solve every question yourself first and then look for solutions. I wish you best learning. Thank you. Thank you so much.